Tonight, we're going to explore one of the oldest and most unsettling questions humanity has ever asked. How big is the universe? At first, the question sounds simple, almost childlike. You look up at the night sky, see stars scattered across darkness, and assume size is merely a matter of measurement. Count enough objects, measure enough distances, build better telescopes. Eventually, the answer should become clear, but the universe does not surrender scale so easily, because the moment you begin measuring the cosmos, something strange happens. Every distance you think is large becomes small. Every boundary you think is far becomes nearby. Every horizon you believe marks an ending becomes merely the beginning of something much larger. And tonight, that is the journey we begin. Not by jumping immediately to galaxies or black holes or the edge of cosmic time. That would be too easy. The true terror of cosmic scale is not discovered in giant leaps. It is discovered step by step through a gradual destruction of intuition. You begin on Earth, a world that feels vast. To an individual human being, Earth is enormous. Oceans separate civilizations, mountains define empires. Deserts isolate cultures for centuries. For most of human history, crossing even a continent was a lifetime achievement. Entire kingdoms rose and fell without ever knowing what existed beyond the horizon. For ancient farmers, the nearby village might as well have been the universe. For sailors, oceans felt infinite. For empires, the world felt conquerable only in fragments. Even today, with aircraft crossing continents in hours and satellites orbiting overhead, Earth still feels big enough to contain everything important to human life. Birth, love, war, invention, memory, civilization. Entire histories unfold on a thin layer of rock and atmosphere, wrapped around a sphere just under 13,000 kilometers across. From space, Earth looks complete, self-contained, a blue world suspended in darkness. Clouds swirl across continents, lightning flashes inside storms. City lights glitter across night-facing hemispheres like neural activity inside a planetary brain. Borders vanish. Politics vanish. Economies vanish. Seen from orbit, humanity becomes invisible. You see the species only through its consequences. Thin scars of light, artificial constellations, a faint technological glow, and even that glow exists only on the surface. This is the first lesson of scale. Human civilization feels immense from the ground. From orbit, it becomes delicate. The cities that feel permanent become microscopic. The roads that connect nations disappear. The tallest skyscrapers ever built become thinner than dust particles on a globe. Your home vanishes. Your city vanishes. Your nation vanishes. And yet, astonishingly, even orbit is still close. Very close. The International Space Station, one of humanity's most ambitious engineering achievements, orbits only about 400 kilometers above Earth. In cosmic terms, that distance is almost nothing. If Earth were the size of a classroom globe, the station would sit barely a finger's width above its surface. That is not deep space. That is atmosphere's doorstep. And here the illusion begins to crack, because most people imagine space as beginning somewhere far away. It does not. Space begins almost immediately. Drive north for a few hours, fly across a country, climb high enough, you are already there. The boundary between human civilization and cosmic wilderness is startlingly thin. A fragile shell of breathable air roughly 100 kilometers thick by conventional definition protects every forest, city, ocean, animal, language, government, religion, dream and memory humanity has ever produced. Everything human exists beneath that shell. Everything beyond it is hostile. No pressure, no oxygen, extreme temperature swings, radiation, vacuum, silence. The entire story of civilization survives inside a film of atmosphere thinner relative to Earth's size than the skin of an apple. That realization changes something fundamental, because suddenly the universe stops feeling like a distant curiosity and starts feeling like an ocean pressing against a glass wall. We are not surrounded by friendly emptiness. We are sheltered from lethal emptiness. And for thousands of years, humanity did not fully understand this. Ancient civilizations mapped stars with astonishing precision. Babylonian astronomers tracked planetary motion. Greek philosophers debated celestial order. Polynesian navigators crossed vast oceans using stellar memory. Islamic astronomers refined mathematical astronomy across centuries. Chinese skywatchers recorded comets and supernovae long before Europe built modern observatories. They understood the heavens mattered. But even the most brilliant early observers lacked one crucial thing: distance. Stars appeared as lights on a dome. Planets wandered across celestial patterns. The sky felt structured, beautiful, perhaps divine, but not deep. Not yet. The night sky hides depth exceptionally well. This may be one of the universe's most effective illusions. Your eyes see brightness, position, colour. They do not see scale. Two stars appearing adjacent in the sky may actually be separated by hundreds or thousands of light years. One may be nearby and faint. Another may be incomprehensibly distant and unimaginably luminous. Your brain flattens all of it into a surface. A ceiling of lights. A cosmic painting. This is understandable. Human perception evolved to judge survival distances. Meters. Hundreds of meters. Perhaps kilometers. Not millions. Not billions. Certainly not cosmic scale. Evolution prepared you to throw spears, track movement, judge weather, read expressions, and detect predators in grass. It did not prepare you to intuit the architecture of space-time. That mismatch between biology and reality is why cosmic scale feels so unnatural. You were not built to understand it. You must construct understanding artificially, with mathematics, with imagination, with instruments, and even then comprehension resists. That resistance is important because tonight's journey is not merely about large numbers. Anyone can say billions or trillions. Numbers alone do not create understanding. The real challenge is psychological. How do you make the incomprehensible feel real? How do you emotionally grasp distances so large that even light struggles to cross them? How do you understand a universe where the fastest thing allowed by physics can spend billions of years in transit? That is the true challenge, not measurement, perspective. And our first step toward that perspective requires leaving Earth behind completely, not metaphorically, not philosophically, physically. We need to travel outward, past the atmosphere, past orbit, past satellites, past the region where human machinery still routinely operates. We must move into true space. Only then does the next illusion collapse, because once Earth shrinks behind us, the first destination seems obvious: the nearest world. The object that has watched humanity since before history. The body that shaped tides, calendars, myths, agriculture, poetry, and religion. The moon. It hangs above us so often that familiarity has made it harmless, comforting even, close enough to feel intimate. But closeness in the night sky is deceptive, and that deception hides one of the first truly disturbing truths about cosmic distance. The moon is not close, not even remotely close by human standards. And once you understand how far away our nearest celestial neighbour truly is, something unsettling happens. The universe becomes much larger than you thought. One obstacle remained. Before we can understand the size of the universe, we must first confront the scale of our own cosmic backyard. The moon feels close because it never leaves us. Night after night it rises over cities, deserts, oceans, forests and mountains, with such consistency that human civilization built part of its sense of time around it. Long before mechanical clocks, long before standardized calendars, people watched lunar phases to measure cycles of planting, migration, ritual, and survival. The moon became more than an object in the sky. It became rhythm. That familiarity creates an illusion of intimacy. You can hold your thumb up at arm's length and cover the moon completely. You can photograph it with a phone. You can watch it rise above rooftops and feel as if it belongs to Earth, almost like an extension of our world rather than a separate celestial body. But scale in space is treacherous. Objects that appear small are not necessarily small. Objects that seem near are not necessarily near. The moon exploits this weakness in human perception almost perfectly, because the average distance to the moon is about 384,400 kilometers. That number sounds large, but numbers rarely produce emotional understanding. The human mind hears hundreds of thousands and simply labels it far. Yet far is not enough. We need something more physical. Imagine driving to the moon. No rockets, no orbital mechanics. Just a car moving continuously at highway speed, perhaps 100 kilometers per hour, without stopping for sleep, fuel, or rest. The journey would take roughly 160 days, nearly half a year. Continuous driving to reach the nearest celestial body. Now imagine commercial aviation. A jet cruising around 900 kilometers per hour would still need more than 2 weeks of uninterrupted flight. 2 weeks, no landings, no refueling, no atmosphere to generate lift, and suddenly something changes. The moon stops feeling nearby, but there is an even better way to visualize the distance, one that astronomers love because it quietly destroys intuition. You can fit every planet in the solar system between Earth and the moon, all of them. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Stack their diameters together, and remarkably, they fit with room to spare. Pause there. Our nearest world is so far away that the combined widths of every planet orbiting the Sun can fit inside the gap. That is not just distance. That is emptiness. And emptiness is the true character of the universe. Humans tend to imagine space as filled with objects, stars, planets, nebulae, galaxies. But the dominant feature of the cosmos is not matter, it is absence, nothingness. Distance is not defined by objects, it is defined by the enormous emptiness between them. That truth became painfully real during the Apollo era. In July 1969, when Neil Armstrong and Buzz Aldrin descended toward the lunar surface, humanity crossed a boundary unlike any before it. This was not merely a technological milestone, it was a psychological rupture. For the first time, humans left Earth's immediate environment and travelled to another world. The voyage took roughly 3 days. 3 days inside a machine smaller than many apartments. 3 days suspended in vacuum. 3 days with Earth shrinking behind them. That shrinking mattered. Astronauts repeatedly described a strange emotional transformation during lunar missions. Earth stopped feeling like home in the ordinary sense and began to feel fragile, small, isolated. No borders, no nations, just a sphere. White clouds drifting over blue oceans, a thin atmosphere glowing faintly around its edge. The famous Earthrise photograph taken during Apollo 8 changed public consciousness for exactly this reason. It showed Earth not as centre, but as island. A tiny island, floating in darkness. For millions of years, humans assumed land was safety, and the unknown lay beyond the horizon. Space reversed that intuition. Suddenly Earth became the only known refuge in an ocean of hostility, and the moon emphasized something even more unsettling. Reaching nearby space was possible, routine even, but deep space remained far beyond our instincts. Because once you arrive on the moon, you encounter a terrifying silence. No wind, no weather, no birds, no sound. Footprints remain for millions of years because nothing erases them. Time itself feels altered. Imagine standing there. Grey dust stretches to a jagged horizon. The sky is black, even in daylight. Shadows are absolute. Above you hangs Earth, luminous and alive, impossibly beautiful. Every human who has ever loved, suffered, built, fought, sung, dreamed or hoped exists on that distant sphere. 7, 8, perhaps 10 billion minds in the future, all there. Not here. You are elsewhere. That word matters. Elsewhere. Because the moon was humanity's first proof that worlds are real places, not decorative lights in the sky. And once worlds become places, a dangerous question emerges. How many more places are out there? That question fueled science fiction long before engineering could support it. Lunar travel inspired dreams of Mars orbital cities, asteroid colonies, and interplanetary civilization. The logic seemed natural. If we reached the moon, surely the rest would follow. But optimism hid a deeper problem. The moon is close only relative to everything beyond it. In truth, it is merely the smallest first step, a local hill mistaken for the mountain range beyond. And this is where the next illusion collapses. Because many people subconsciously imagine the solar system as compact, they see classroom posters with planets lined neatly beside the sun. Distances are compressed to fit on paper. Orbits look orderly and manageable. Earth feels comfortably positioned among neighbouring worlds. Those diagrams are useful. They are also profoundly misleading. If Earth were reduced to the size of a marble, the moon would orbit roughly a metre away. That feels manageable. But now scale the sun properly. At that same scale, the sun becomes a giant sphere over 100 metres wide. And Earth would orbit roughly 11 kilometres away. Not metres, kilometres, with mostly nothing in between. This is where human intuition begins failing again, because the moon taught us that nearby space is vast. The solar system will teach us something worse. The moon is still part of home, still gravitationally intimate with Earth, still inside a local neighbourhood. The real emptiness begins when we move beyond the Earth-Moon system, beyond orbit, beyond familiar worlds, into the vast architecture of the Sun's domain. And there the universe introduces a much larger deception. The planets that seem clustered together in diagrams are separated by gulfs so immense that even light needs hours to cross them. Distance was never the only problem. The deeper problem was scale compression. Our minds keep shrinking the cosmos to something comfortable. The universe keeps refusing, and as we prepare to leave the moon behind, another unsettling realization emerges. If our nearest celestial neighbour already feels impossibly far, what happens when we attempt to cross the solar system itself? That is where scale stops being merely large. That is where it begins becoming alien. The moon taught us that nearby in space does not mean close. But the solar system teaches something far more disturbing. Nearby may not mean reachable. This is the illusion most people carry without realizing it. Since childhood, you have probably seen the same image dozens, perhaps hundreds of times. A bright sun on one side, 8 planets arranged in graceful sequence, small inner worlds, giant outer worlds, rings around Saturn, blue Neptune at the edge, clean orbital paths, elegant geometry, a cosmic family portrait. The image is useful. It is also false in one important way. Not false in structure, false in feeling. Because the diagram compresses distance so aggressively that it quietly trains your brain to believe the solar system is crowded. It is not crowded. It is almost empty, beyond comprehension. Imagine trying to build a scale model that preserves both planetary size and distance accurately. The problem becomes absurd almost immediately. If the sun were the size of a large front door, Earth would be about the size of a peppercorn. That peppercorn would orbit more than 100 meters away. Already the space between them dominates the model. Now continue outward. Mars sits farther still, another tiny speck, separated by additional emptiness. Then comes the asteroid belt, often imagined as a dangerous field of tumbling rocks, forcing spacecraft to weave through constant collisions. Reality is stranger. The asteroid belt is mostly empty space. Even large asteroids are separated by enormous distances. A spacecraft crossing the belt is extraordinarily unlikely to encounter anything at all. Once again, cinema misled us, because emptiness is difficult to dramatize. But emptiness is the story. Cross the belt and you reach the giant planets. Jupiter dominates so large that more than 1,300 Earths could fit inside it. Storms larger than continents churn through its atmosphere. Radiation belts could destroy unshielded electronics. Moons orbit it like miniature solar systems, and yet even Jupiter is far, very far. Light, the fastest thing allowed by physics, takes around 43 minutes to travel from the Sun to Jupiter. Think about that. Sunlight touching Jupiter left the Sun merely 3/4 of an hour earlier. The warmth illuminating its cloud tops is already old. By the time sunlight reaches Saturn, more than 79 minutes have passed. To Uranus, nearly 3 hours. To Neptune, over 4 hours. We are still talking about our local neighbourhood. Still inside the Sun's gravitational empire. Still nowhere near interstellar space. This is the solar system illusion. The planets feel like destinations arranged in sequence, as though civilization could simply advance outward step by step. First the Moon, then Mars, then Jupiter's moons, then Saturn, then beyond. But the distances do not scale gently, they explode. And propulsion becomes the first brutal reality check. Chemical rockets carried humanity to the moon, but chemical propulsion has limits. Enormous power is required merely to escape Earth's gravity. Every kilogram of payload demands fuel. More fuel adds mass. More mass demands more fuel. Engineering begins fighting mathematics. This problem haunted every major space program. It still does. Even the most powerful operational rockets are not fast by cosmic standards. Fast compared to aircraft, certainly. Fast compared to artillery, yes, but not fast compared to the scale of space. Take New Horizons, launched in 2006. It became one of the fastest spacecraft ever launched from Earth, assisted by a gravity boost from Jupiter. Even at extraordinary speed, it took more than 9 years to reach Pluto. 9 years. A child entering elementary school at launch could approach adulthood before arrival. And Pluto is not the edge. That may be the most unsettling part, because for generations Pluto represented the distant frontier, the lonely outer marker, the final planet. the symbolic edge of the solar system. But Pluto was never the edge, not even close. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies, dwarf planets, and ancient debris left over from planetary formation. Beyond that lies something even stranger, a hypothetical region so vast it borders on absurdity. The Oort cloud. This is where scale begins to mutate into something almost impossible to visualize. The Oort cloud is believed to be a spherical reservoir of icy objects surrounding the solar system, source of many long-period comets. It may extend thousands to perhaps 100,000 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun. One Earth-Sun distance, about 150 million kilometers. Now multiply that by tens of thousands. The numbers become monstrous. At the outer edge of the Oort cloud, the Sun would no longer dominate the sky as a blazing star. It would appear as an unusually bright point among many others. That is when something psychological happens. Home disappears. Not physically. Perceptually. From Earth, the Sun defines existence. It drives climate, agriculture, weather, biology, energy. Nearly every ecosystem ultimately depends on it. But at great enough distance, the Sun becomes just another star. This realization is deeply unsettling because it destroys hierarchy. We assume our star matters cosmically because it matters to us. The universe disagrees. Our Sun is locally essential, cosmically ordinary. One star among hundreds of billions inside the Milky Way. One star among perhaps trillions of galaxies. The solar system illusion collapses completely here. What felt large from Earth becomes tiny from interstellar perspective. And this shift reveals a pattern we will encounter again and again tonight. Every scale feels absolute until a larger scale absorbs it. Earth felt vast until orbit. The Earth-Moon system felt large until the solar system. The solar system now begins to feel provincial, small, contained, and something else becomes apparent. The problem is no longer merely distance. Time has entered the story, because travel across the solar system already spans years and decades using our best machines. Human lifetimes begin mattering. Mission planning becomes generational. Careers begin and end before data returns. Consider Voyager 2. Launched in 1977. When it left Earth, the personal computer era had barely begun. The internet as we know it did not exist. Most modern viewers were not yet born. And yet Voyager still travels, still transmitting, still moving outward through darkness. Nearly half a century later, its journey forces an uncomfortable question. If crossing our own solar system can consume decades, what happens when we aim for another star? That question changes everything. Because until now, every destination remained under the Sun's influence. Every planet, every moon, every comet, every probe, still home. The next step is different. The next step means leaving the solar system entirely, leaving sunlight's empire, crossing into interstellar space, and there a terrifying truth waits. The nearest star is not merely far, it is so far that even the solar system begins to look small. For nearly all of human history, the Sun defined reality. It rose, it set. It governed seasons, agriculture, migration, hunger, and survival. Civilizations worshipped it, feared it, measured time through it, and built entire cosmologies around its movement. Even after astronomy transformed myth into physics, the Sun retained its central role. It remained the engine of life, the gravitational anchor of every world humanity had ever known. So there is something deeply unsettling about a place where sunlight stops feeling dominant, a place where the Sun no longer rules the sky. To understand that place, we follow a machine, not a starship, not a future vessel. A small robotic messenger launched by late 20th century engineers who understood that they would never personally witness the final chapters of its journey. Voyager 1 lifted from Earth in September 1977. Its twin, Voyager 2, launched weeks earlier. Their original purpose was ambitious but still local. Exploit a rare planetary alignment to visit the giant outer planets using gravity assists. It was one of the most elegant acts of celestial engineering in human history. The alignment mattered because gravity can become propulsion. A spacecraft falling into a planet's gravity well can steal a tiny fraction of that planet's orbital momentum, leaving with greater speed than it arrived. To the spacecraft, the planet becomes a moving slingshot. This technique allowed the Voyagers to do something chemical rockets alone could not achieve. Travel farther, travel faster, travel longer. And they succeeded. beyond expectation. Voyager 1 visited Jupiter and Saturn. Voyager 2 achieved something even more extraordinary, visiting Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft ever to visit the ice giants. The images changed humanity's relationship with the outer solar system. Storms the size of worlds, ring systems sculpted by gravity, frozen moons with fractured crusts, volcanic eruptions on alien landscapes. Until then, the outer planets were distant abstractions. The Voyagers turned them into places. But their story did not end there, because once the planetary tour concluded, the spacecraft kept moving outward, always outward, past the known planetary frontier, into regions where human intuition begins to fail again. Because beyond the outer planets lies something that is easy to describe and extremely difficult to imagine. The heliosphere. This is not a physical wall, not a shell you can see. It is more subtle. The sun continuously releases a stream of charged particles flowing outward in all directions. This solar wind expands through space, carrying magnetic influence far beyond the planets. For immense distances, the sun's presence is not just visible through light, but physically active through this flowing plasma. In effect, the solar system has weather, not atmospheric weather, stellar weather, an expanding bubble carved into interstellar space. That bubble is the heliosphere. As long as you remain inside it, you are still inside the sun's dynamic influence, still under solar weather, still in a meaningful sense, home. But bubbles end, and that ending is not clean. As the solar wind pushes outward, it eventually encounters the thin material between stars, the interstellar medium. Pressure builds, flow slows, boundaries form, regions of turbulence emerge. The edge becomes less like a border checkpoint and more like a storm front between two invisible oceans. This is where the Voyagers were headed, not intentionally at first, but inevitably. Year after year, decade after decade, they crossed regions no human-built machine had ever entered, and with every billion kilometers, sunlight weakened. This is where scale becomes emotional. At Earth's orbit, sunlight feels natural because it is overwhelmingly present. It illuminates landscapes, powers climate, and dominates vision. Even on cloudy days, the sun shapes every visual experience. Move outward, and brightness falls rapidly, not gradually enough for comfort, but mathematically. Double the distance from the sun, and sunlight drops to 1/4. Triple the distance, 1/9. 10 times farther, 1/100th. The decline is ruthless. By Jupiter, daylight resembles a dim, overcast afternoon on Earth. By Saturn, the sun still shines, but weaker, smaller, colder. By Neptune, sunlight is roughly 900 times weaker than on Earth. 900. At noon, on Neptune, the sun would no longer dominate the sky as it does here. It would look more like an intensely bright star, still visible, still powerful, but diminished. That word matters. Diminished. Because diminishing sunlight means diminishing familiarity. Human intuition depends on familiar sensory anchors. Day and night, warmth and shadow, sky and horizon. The farther you travel from the sun, the more those anchors dissolve. Eventually the sun becomes just a bright point. Eventually warmth becomes memory. Eventually even the concept of solar neighborhood starts feeling misplaced. And then something historic happened. In August 2012, after nearly 35 years of travel, Voyager 1 crossed a boundary humanity had never crossed before. It entered interstellar space. The phrase sounds dramatic, but its emotional meaning runs deeper than the words suggest. For the first time in human history, something built by our species left the sun's protective bubble and entered the space between stars. A machine from Earth crossed into cosmic wilderness. That achievement forces a profound perspective shift. Voyager 1 was moving at roughly 17 kilometers per second. Extraordinary by engineering standards. And yet, even at that speed, reaching interstellar space took decades. Decades just to leave home. This is where the central illusion collapses. Many people casually imagine the solar system as space, and interstellar travel as the next logical extension. But the heliosphere teaches something harsher. The solar system is not a point. It is a vast domain with soft boundaries extending far beyond the planets. Leaving it is not like leaving a city. It is like leaving an empire, and the deeper implication is difficult to ignore. If escaping our own star's domain takes nearly half a century with some of our fastest probes, what does that imply about reaching another star? The answer is disturbing, because interstellar space is not filled with destinations. It is filled with distance. The space between stars is not merely large, it is, mostly, nothing. Cold gas, Sparse particles, darkness. Silence. Light from distant suns crossing unimaginable emptiness, and in that darkness, Voyager continues. A machine carrying a golden record curated by Carl Sagan and his team. Sounds of Earth, human greetings, music, encoded traces of civilization, a message without guaranteed recipient, a bottle thrown into a cosmic ocean. That image is haunting for a reason, because it reveals something essential about humanity. Even when confronting incomprehensible scale, we send stories, signals, artifacts, proof that we existed. But there is one problem. Voyager has not gone very far. That may be the most unsettling truth of all. Despite nearly 50 years of uninterrupted travel, Voyager has only begun to enter the vast gulf between stars. Its journey feels heroic from human perspective. Cosmically, it has barely moved. And that leads to the next question. If our most enduring interstellar messenger has spent half a century crossing only the outer threshold of home, how far away is the nearest star? The answer will permanently alter your sense of distance. There is a dangerous phrase in astronomy. Nearest star. It sounds comforting, manageable. Human language quietly betrays us here, because the word nearest suggests accessibility. We hear nearest and imagine something adjacent, something that lies just beyond the edge of our current capability. A difficult destination perhaps, but still a destination. The universe has no obligation to honour that intuition, because the nearest star beyond our sun is not close, not remotely. It is Proxima Centauri, a dim red dwarf gravitationally bound to the Alpha Centauri system. Invisible to the naked eye, modest in brightness, unremarkable by stellar standards. If cosmic history were written as a grand catalogue of stars, Proxima would barely receive a footnote, and yet it matters enormously. Because Proxima is the first wall, the first true test of whether humanity can ever become an interstellar civilization. Its distance is approximately 4.24 light-years. Again, the number sounds manageable until language collapses. A light-year is not a measure of time. It is a measure of distance. The distance light travels in 1 year. Light moves at about 300,000 kilometers per second every second. It circles Earth more than 7 times in a single second. It travels from Earth to the Moon in roughly 1.3 seconds. It reaches the Sun in about 8 minutes. This is the fastest speed allowed by known physics. Nothing carrying information outruns light. Nothing. Now let light travel for 1 full year without stopping, without slowing, through uninterrupted vacuum. That distance equals about 9.46 trillion kilometers. Trillion. Not billion, trillion. Now multiplied by 4.24. That is the distance to the nearest star. More than 40 trillion kilometers. The human brain does not process this naturally. So once again we need analogy. Imagine shrinking the solar system. Suppose the sun were reduced to the size of a tennis ball placed in the center of a city square. Earth becomes a grain of sand orbiting roughly 26 meters away. That already feels spacious. But where is Proxima Centauri? Not across the square, not across the city, not even across the country. At that scale, the nearest star would sit thousands of kilometers away, roughly the distance between major continents, with almost nothing in between. This is the first great terror of interstellar space. Not stars, not radiation, not exotic physics. Emptiness. Nearly total emptiness. Stars are islands, and the ocean between them is vast beyond instinct. This changes the story of space exploration immediately. Everything humanity has accomplished in space so far, every satellite launch, every moon landing, every Mars rover, every planetary probe, has occurred inside a region that now begins to feel microscopic compared with interstellar distance. The Moon. Seconds at light speed. Mars. Minutes. Neptune. Hours. Proxima. Years. Not for spacecraft, for light. That distinction matters, because if light itself requires more than 4 years, then every slower technology becomes painfully inadequate. Let us ask the obvious question. What if we sent Voyager 1 to Proxima Centauri? Voyager travels around 17 kilometers per second, an extraordinary engineering achievement. At that speed, reaching Proxima would take approximately 75,000 years. Pause there. 75,000 years. When Voyager launched in 1977, humanity had microprocessors, color television, and early space probes. 75,000 years ago, humans painted caves, hunted megafauna, and lived in Paleolithic societies. Entire civilizations rise and disappear inside that time span. Agriculture appears, empires rise, languages evolve, religions emerge. Science is born. Industry transforms civilization. Digital networks reshape humanity, and still the spacecraft would not arrive. That is not a transportation problem. That is a civilizational problem. Suddenly the question changes. The challenge is no longer, can we build a faster spacecraft? It becomes something much deeper. Can civilization remain coherent long enough to complete such journeys? Because distance introduces time, and time introduces history. History introduces instability. This is the real barrier between stars. Not simply propulsion. Continuity. Human societies do not remain static for millennia. Governments collapse. Languages mutate. Beliefs shift. Institutions decay. Economies transform. Even memory erodes. Imagine a mission launched today requiring 10,000 years to complete. Who owns it? Who funds it? Who remembers why it began? Would descendants still care? Would they even understand the original language? A mission longer than civilization becomes something else entirely. It stops being exploration. It becomes inheritance. This realization disturbed scientists long before spacecraft made interstellar ambitions seem practical. In the 20th century, thinkers began confronting a painful truth. Crossing the gap between stars might demand more than engineering breakthroughs. It might require reinventing civilization itself. But perhaps there was another way. Perhaps the problem was not society. Perhaps the problem was speed. Could we simply travel much faster? The logic feels irresistible. If Voyager takes 75,000 years, then build something 100 times faster, 1,000 times faster. Keep accelerating until the journey becomes practical. For a moment, this seems reasonable. Then physics intervenes. Speed is expensive, not financially, energetically. Kinetic energy rises with velocity. Faster travel demands vastly more energy, especially as speeds approach meaningful fractions of light speed. The requirements become brutal. A spacecraft moving at 10% of light speed would cross to Proxima in roughly 40 years. 40 years. Now the destination feels human. A career. A lifetime. A mission someone could launch and personally witness conclude. That sounds like success. But there is a problem. Reaching 10% of light speed is unimaginably difficult. At that velocity, even tiny dust particles become deadly. Microscopic grains strike with explosive force. Shielding becomes massive. Mass demands energy. Energy demands infrastructure. Infrastructure demands civilization-scale industry. And one obstacle remains even more fundamental: Einstein. This is where cosmic distance stops feeling like an engineering challenge and begins feeling like a confrontation with the architecture of reality itself. Because for centuries, humanity assumed speed had no ultimate ceiling. Faster ships, stronger engines, better fuel. Progress seemed linear. Then in the early 20th century, one physicist changed the rules. Albert Einstein showed that space and time were not fixed backgrounds, but interconnected structures, and hidden inside that structure was a boundary, an absolute limit, the speed of light. The universe had imposed a speed limit on causality itself. No signal. No object with mass, no spacecraft, no civilization could simply decide to go faster. And with that discovery, interstellar travel became something much stranger than humanity expected. Distance was not the only enemy. Reality itself had constraints. The nearest star was no longer just far away. It was protected by the laws of physics. The story did not end there. In fact, this is where it truly begins. Because once Einstein drew the boundary, humanity faced a terrifying question. What happens when the obstacle is not technology, but nature itself? Once the nearest star became a real destination rather than an abstract point of light, humanity responded the way it often does when confronted with a difficult frontier. It began designing machines. If distance was the problem, build faster ships. If time was the problem, build stronger engines. If interstellar space demanded extraordinary travel, then perhaps extraordinary engineering could bridge the gap. This optimism was not naive. It emerged from history. For centuries, seemingly impossible transportation barriers had repeatedly fallen. Oceans that once took months to cross became routine shipping lanes. Continents that required dangerous expeditions became connected by rail. Flight compressed hemispheres into hours. Rockets lifted humans beyond Earth entirely. Progress trained civilization to believe that enough engineering eventually defeats any distance. The stars seemed like the next logical step. So scientists, military planners, physicists, dreamers and futurists began sketching the first serious starships. Not fictional ones, real proposals. Mathematical. Engineered. Calculated. And at first, the future looked promising. Because chemical rockets had already revealed one truth: propulsion worked. Motion through vacuum was not the problem. Newton's laws were reliable. Thrust changed velocity. Velocity changed trajectory. Trajectory changed destiny. The question was scale. How much energy would be needed to push a meaningful spacecraft to meaningful fractions of light speed? That question produced one of the first harsh lessons in interstellar engineering. Everything becomes fuel. On Earth, fuel feels separate from payload. Cars carry passengers and cargo, while fuel sits in a tank. Aircraft carry people, luggage, and fuel as distinct categories. Rockets destroy that intuition. In rocketry, fuel dominates everything. A spacecraft accelerating by expelling propellant must carry the reaction mass required for acceleration. More velocity demands more propellant. More propellant increases mass. More mass demands even more propellant. The mathematics spiral rapidly. This problem is known through the tyranny of the rocket equation. Tyranny is the correct word, because it behaves mercilessly. At a modest speed increase and fuel requirements climb steeply. Demand extreme speed and fuel mass explodes into absurdity. Engineers quickly realized something uncomfortable. Chemical propulsion would never take humans to the stars. Never. Not because chemical rockets are weak by human standards, because stars are too far by cosmic standards. So attention shifted. If chemistry was insufficient, perhaps atoms could help. Nuclear energy changed the 20th century by revealing a brutal truth about matter. Tiny amounts of mass contained staggering energy. This inspired radical thinking. In the late 1950s and early 1960s, during the height of the Cold War, engineers pursued one of the strangest propulsion concepts ever seriously studied. General Atomics developed a concept called Project Orion. Its logic was shocking in simplicity. Use nuclear bombs as propulsion, not metaphorically. Literally. A massive spacecraft would eject nuclear explosives behind itself. Each detonation would create a pulse of plasma. A giant pusher plate with shock absorbers would absorb the blast, converting repeated explosions into acceleration. Bomb. Push. Bomb. Push. Again and again. The concept sounds absurd. It was also disturbingly plausible. Calculations suggested Orion could deliver extraordinary performance, huge payloads, massive ships, potentially thousands of tons launched into deep space. Some designs even imagined interplanetary or interstellar missions. For a moment, humanity glimpsed brute force star travel. Build a city-sized spacecraft, detonate nuclear explosions behind it, ride controlled apocalypse into space. It solved one problem beautifully: energy. Then, reality intervened. There were several fatal flaws. Launching nuclear pulse ships from Earth posed catastrophic safety risks. Thousands of nuclear devices would need manufacturing, storage, transport, and controlled detonation. Fallout alone made atmospheric launch politically toxic. International treaties restricting nuclear tests further strangled feasibility. But the deepest problem was not political, it was scale. Even Orion, spectacularly powerful by engineering standards, struggled against interstellar distances. The numbers improved. The stars did not get closer, so scientists dreamed bigger. If fission bombs were insufficient, perhaps fusion could help. Fusion powers stars. Hydrogen nuclei, merging into heavier elements, releases extraordinary energy. The sun shines because fusion converts mass into light continuously over billions of years. If humanity could control fusion efficiently, propulsion could reach entirely new regimes. This inspired one of the most ambitious starship studies ever attempted, Project Daedalus. In the 1970s, members of the British Interplanetary Society undertook a serious design study for an unmanned interstellar probe. Their target, Barnard's star, another nearby stellar system. Daedalus was not fantasy. It was grounded in known physics, extrapolated engineering, and disciplined assumptions. The design was staggering. A two-stage fusion-powered spacecraft weighing tens of thousands of tons. Pellets of fusion fuel ignited repeatedly. Gigantic engines. Enormous fuel reserves. No crew. No luxury. No comfort. Pure velocity. In theory, Daedalus could approach roughly 12% of light speed.
12%.
That was extraordinary. At such velocity, nearby stars moved from impossible to merely difficult. Human civilization felt closer to interstellar capability than ever before. Then another obstacle emerged, one that engineers had underestimated. Interstellar dust. Space looks empty. It is not completely empty. That distinction matters enormously. Even the sparse medium between stars contains atoms, gas plasma, and microscopic particles. At ordinary spacecraft speeds, such particles are mostly irrelevant. At relativistic speeds, they become weapons. A grain of dust, no larger than sand, impacting a spacecraft at significant fractions of light speed, releases energy comparable to explosives. Repeated impacts become erosion. Erosion becomes structural threat. Shielding becomes mandatory. Shielding adds mass. Mass increases energy requirements. Energy increases infrastructure demands. The spiral returns. Again and again, every solution revealed deeper complexity. This pattern became painfully familiar. Attempt. Hope. Fatal flaw. Bigger challenge. Humanity could build more powerful engines, but every gain exposed hidden enemies. Fuel. Massachusetts. Heat. Radiation. Impact. Reliability. Scale itself. And yet, one assumption remained mostly untouched. Everyone still believed the problem was propulsion. Build a sufficiently powerful engine, and the stars become reachable. But what if propulsion was not the deepest limitation? What if even a perfect engine would fail? This question became unavoidable as 20th century physics matured, because while engineers wrestled with rockets and reactors, theoretical physics had already uncovered something much more fundamental. The universe had a speed limit, not a practical speed limit, not a technological one. An absolute one. This changed everything. Because once velocity approaches light speed, strange things happen. Energy requirements cease growing linearly, they rise brutally. Relativity reshapes motion itself. Each increment of speed becomes harder than the last. 10% of light speed is difficult. 50% becomes vastly harder. 90% becomes extraordinary. 99% approaches absurdity. The closer you move toward light speed, the more the universe resists, as though reality itself pushes back. This resistance is not mechanical, it is structural, built into space-time. And that realization forced humanity to confront an unsettling possibility. Perhaps the stars were not meant to be crossed casually. Perhaps cosmic scale was not merely large. Perhaps it was defended, not by hostile aliens, not by engineering limitations alone, but by the architecture of the universe. One obstacle remained. To understand why faster ships kept failing, we must understand the law no engine can ignore. The law Einstein revealed, the relativity war. In 1905, a young patent clerk working in Bern published a paper that would permanently alter humanity's relationship with space-time, motion, and reality itself. His name was Albert Einstein. At the time, Einstein was not yet the cultural icon history would later create. He was not the white-haired symbol of genius recognized across the world. He was an outsider to academic power, working outside the traditional centers of physics, while thinking about questions that many considered abstract curiosities. But abstraction can change civilization. Einstein began with a deceptively simple question. What would happen if you chased a beam of light? The question sounds almost poetic, yet it exposed a contradiction buried inside 19th century physics. Classical intuition suggested velocity should add naturally. If a train moves forward and a passenger walks toward the front, the passenger's speed relative to the ground increases by the train speed plus walking speed. Simple, obvious, human. But light refused to behave that way. Experiments increasingly suggested something deeply strange. No matter how observers moved, light speed remained constant. Constant. Not approximately. Exactly. This result was profoundly unsettling, because it implied something impossible under ordinary intuition. If everyone measures light moving at the same speed, regardless of their own motion, then something else must change. Something fundamental. Einstein realized what had to give. Space and time themselves. This was the beginning of special relativity, and with it came one of the most extraordinary discoveries in scientific history. Time is not absolute. Distance is not absolute. Simultaneity is not absolute. These things depend on motion. The universe is stranger than common sense allows. For everyday life, this strangeness hides because human velocities are tiny compared to light speed. Cars, aircraft, bullets, even rockets remain slow in relativistic terms. At these speeds, classical intuition works well enough. Cosmic travel is different. At interstellar velocities, relativity stops being subtle. It becomes dominant. This is where the relativity wall emerges. It is not a physical barrier. No glowing shield surrounds stars. No cosmic checkpoint blocks spacecraft. The wall is mathematical and therefore inescapable. The closer an object with mass moves toward light speed, the harder further acceleration becomes. Not slightly harder, exponentially harder. Each added fraction of velocity demands disproportionately more energy. The cost escalates brutally. Imagine pushing a spacecraft to 10% of light speed. Already difficult. 20% becomes much harder. 50% demands extraordinary energy. 90% becomes civilization scale. 99% approaches absurdity. 99.9% becomes something close to unimaginable. Every decimal point near light speed becomes expensive beyond intuition. This is why the speed of light is not merely very fast. It is a boundary condition of reality, a limit woven into causality itself. Nothing carrying mass crosses it. That single fact transformed interstellar ambition. Before relativity, faster ships felt like an engineering race. After relativity, they became a confrontation with the laws of existence. And the implications went deeper than propulsion, because Einstein's equations revealed something even stranger. Time itself bends under speed. This phenomenon is called time dilation, though the phrase understates its emotional impact. Suppose a spacecraft travels at extremely high relativistic speed toward another star. To observers on Earth, the journey may require decades or centuries, but for travelers aboard the ship, time passes more slowly relative to Earth. The travelers age less. From their perspective, the trip becomes shorter. This sounds like a loophole. Perhaps it is. For the crew, extreme relativistic travel could make distant stars reachable within human lifetimes. A 100 light-year journey might feel dramatically shorter on board, depending on velocity. At first, this seems like salvation. Then, the deeper consequence emerges. Earth keeps aging. Civilization continues. History advances. The travelers may reach distant stars alive, but the society they left behind may be transformed beyond recognition. Imagine departing Earth at relativistic speed for a mission that feels like 10 years on board. You return. Centuries have passed. Everyone you knew is gone. Languages evolved. Governments vanished. Cultures transformed. The home you left survives only in archives. This is where interstellar travel stops being transportation. It becomes temporal displacement, a one-way migration into the future. Human intuition resists this because we treat travel as spatial relocation. Relativity forces a harsher truth. At cosmic scales, travel becomes movement through both space and time in asymmetric ways. You do not merely cross distance, you detach from shared history. This realization altered science fiction, futurism, and philosophical thinking alike. Interstellar travel no longer meant heroic explorers simply reaching distant stars. It implied fractured timelines, separated civilizations, asynchronous histories. Two human societies, separated by relativistic journeys, might remain biologically related while becoming historically alien. And even this did not solve everything, because reaching relativistic speed still requires monstrous energy. Einstein gave physics another famous equation, one perhaps more culturally recognizable than any in history. E equals mc squared. Mass and energy are equivalent. This equation quietly explains both nuclear power and relativistic difficulty. The speed of light squared is enormous. That means tiny amounts of mass correspond to extraordinary energy. It also means accelerating mass toward light speed involves energy scales far beyond ordinary engineering. To push a meaningful spacecraft to relativistic velocity, civilization may need energy infrastructure on planetary or even stellar scales, not large rockets, large civilizations. This changes the ladder of difficulty again. The problem is no longer just technology, then not just engineering, now civilization. What kind of society can command such energy? What economy supports it? What political system coordinates it? What culture sustains commitment across generations? The challenge keeps expanding. Every answer enlarges the problem. This is the pattern the universe keeps imposing. And yet, humanity refused surrender. If brute force speed faced the relativity wall, perhaps there were other strategies. Perhaps we did not need individual humans to make the journey quickly. Perhaps the solution was social rather than physical. a radical idea began emerging. If one human lifetime is too short to cross interstellar distances, what if the travelers simply stop expecting arrival within one lifetime? What if the ship itself becomes civilization, not a vehicle, a world, a moving society, a city crossing darkness, a culture in transit, children born aboard, grandchildren inheriting the journey, generations living and dying between stars? This idea was both elegant and terrifying because it bypassed one obstacle while creating many more. The relativity wall said you cannot casually outrun physics. Very well, do not outrun it, endure it. But that solution introduced a question even more unsettling than energy or speed. Could humanity survive itself long enough to reach another star? Not biologically, socially, psychologically, civilizationally. Because machines can endure vacuum, can societies endure isolation? A spacecraft can cross centuries. Can meaning? That question opened one of the most profound chapters in humanity's confrontation with cosmic scale. The ship was no longer the hardest part. The people inside it were. Once the relativity wall became unavoidable, humanity faced a brutal choice: accept confinement to the solar system, or change the definition of travel itself. For centuries, exploration had followed a familiar pattern. A traveller departs, journeys through danger, reaches a destination, and returns with knowledge. The structure is deeply human because it aligns with a human lifespan. Exploration feels meaningful when departure, discovery, and return fit inside one life. Interstellar space destroys that structure. The stars do not care about biological timelines. Even with advanced propulsion, many journeys remain too long for conventional exploration. If physics refuses to shorten the voyage enough, perhaps civilization must adapt to the voyage, rather than demand the voyage adapt to civilization. This is the logic behind one of the most extraordinary ideas ever proposed: the generation ship. Tonight, we have arrived at a concept that feels less like engineering and more like myth. Picture it: a vessel drifting through interstellar darkness, no windows showing nearby worlds, no destination visible to the naked eye, only distant stars. A machine so vast it contains not merely crew, but society. Artificial ecosystems, agriculture, homes, schools, governance, birth, death, memory. Everything required not for a mission, but for civilization. This is not a spacecraft in the traditional sense. It is a world in motion, a moving civilization, a planet substitute built by human hands. The idea emerged in the 20th century as scientists and futurists became increasingly honest about interstellar timescales. Writers such as Robert H. Goddard, later thinkers like Freeman Dyson, and numerous space settlement theorists explored variations of this concept. The core insight was simple: if no traveller can survive the full journey, let the journey outlive the traveller. Children born on board inherit the mission. Their children inherit it from them. Generations pass, centuries pass, perhaps millennia. Eventually, descendants reach another star. At first glance, the idea feels plausible. Technically difficult, yes, but plausible. Build a sufficiently large, closed ecosystem. Recycle air, water, nutrients. Maintain genetic diversity. Preserve knowledge. Sustain social order, keep the vessel functioning. If humanity can build cities, perhaps it can build one that travels. Then the deeper problems appear, and once again, the challenge expands. Because engineering was only the first layer. A generation ship is not primarily a transportation problem, it is a civilization problem. Start with biology. Closed ecosystems are fragile. Earth hides this fragility because it is enormous and buffered by planetary-scale feedback systems. Oceans regulate temperature, atmosphere distributes heat, geological cycles recycle minerals, biodiversity creates resilience. Artificial ecosystems lack such redundancy. A disease outbreak inside a closed biosphere becomes existential. Crop failure becomes catastrophic. Microbial imbalance threatens survival. Resource contamination spreads through every subsystem. Nothing is truly disposable in a closed world. Everything circulates. Waste becomes resource. Failure becomes system-wide. This is why small biosphere experiments on Earth revealed something profound. Creating stable artificial ecosystems proved far harder than expected. Tiny imbalances amplified. Biological complexity resisted simplification. Earth works not because ecosystems are simple. Earth works because ecosystems are impossibly complex. Replicating that complexity inside metal walls became a daunting challenge. But biology was only the beginning. Psychology emerged as something even harder. Imagine being born aboard a generation ship. You did not choose the mission. You did not launch. You did not consent to interstellar exile. You inherited it. Your entire reality consists of corridors, habitats, artificial parks, controlled lighting, recycled air, and stories about a distant origin called Earth. Earth is not memory. Earth is mythology, a place ancestors describe, a blue world no living person has seen. How long before mythology changes? How long before mission purpose erodes? This is where social stability becomes central. Civilizations survive not merely through resources, but through shared meaning. Meaning coordinates sacrifice. Meaning justifies hardship. Meaning binds generations. A generation ship therefore requires something extraordinary, a culture capable of preserving mission continuity across centuries. Consider human history. Empires collapse within centuries. Religions split. Languages transform. Political systems mutate. Records burn. Institutions decay. Revolutions rewrite values. Even when knowledge survives, interpretation changes. Now isolate a society completely. No external trade, no migration, no neighbouring cultures, no new land, no escape. Conflict becomes claustrophobic. Governance becomes existential. Every political failure compounds. A civil war inside a generation ship is not merely tragic, it may be terminal. This is why some theorists concluded the hardest engineering challenge was governance, not engines, institutions. What constitution survives centuries? What legal system prevents tyranny? What social architecture balances freedom with survival? Too much control creates oppression. Too little creates instability. The ship must preserve order without destroying humanity's psychological need for autonomy. This balance is extraordinarily delicate. And then comes identity. This may be the deepest problem of all. Who are the passengers? Explorers, colonists, prisoners, descendants of volunteers, citizens of a new state. A generation ship may begin as a mission. It may evolve into a civilization with its own culture, myths, rituals, art, and politics. At that point, arrival itself becomes complicated. Suppose the ship reaches its destination after 500 years. Should the descendants colonize? Do they want to? What if the ship has become home? This sounds hypothetical. Yet it reveals a philosophical fracture. We assume arrival is success. But success according to whom? The launch generation, or the living generation? A mission across centuries creates competing moral timelines. The dead define purpose. The living experience consequence. And that tension may become unavoidable. Some thinkers proposed authoritarian structures to preserve continuity. Others favoured democratic resilience. Some imagined AI governance systems mediating conflict. Others feared algorithmic control becoming permanent technocracy. Every solution created new dangers. Attempt, hope, fatal flaw, bigger challenge. The pattern continued. Yet generation ships revealed something profound. The obstacle between stars was no longer distance alone. Humanity had climbed another level of difficulty. Technology became engineering. Engineering became biology. Biology became psychology. Psychology became society, and society approached civilization. The ladder was ascending. But one problem remained underappreciated. Even if a generation ship succeeds socially, another barrier persists. Communication. Civilization does not exist in isolation. Human societies depend on exchange, ideas, culture, trade, language, knowledge. What happens when worlds cannot speak in real time? What happens when distance turns conversation into archaeology? Because even if humanity settles multiple star systems, the speed of light still rules. Messages cannot outrun causality. Signals crossing interstellar distances arrive years later. Replies return years after that. A conversation becomes decades. Diplomacy becomes patience. Relationships become delayed history. And that raises a disturbing possibility. Even if humanity reaches the stars, can humanity remain one civilization? Or does distance inevitably fracture us into separate histories? The ship solved travel. It did not solve separation. The deeper problem remained. Space was not only large, It disrupted connection itself. Civilization is built on communication. This sounds almost too obvious to matter, yet communication shapes nearly every layer of human society. Families survive through conversation, markets function through information, governments coordinate through signals, science advances through exchange, culture persists through shared stories. Remove communication, and society begins fragmenting. Delay communication, and something more subtle happens. Trust changes. Coordination slows. Identity weakens. Shared reality becomes harder to maintain. For most of human history, communication delay defined civilization. A message carried by horse, ship, or courier could take weeks, months, even years. Empires were limited not only by armies, but by information speed. Orders issued by rulers often arrived too late. Borders became unstable. Distant provinces drifted culturally and politically. Then communication accelerated. The telegraph changed governance. Radio compressed continents. Satellites connected hemispheres. Fiber optics turned oceans into milliseconds. Digital networks transformed civilization into something increasingly synchronized. Modern society quietly depends on near-instant communication. Financial markets react in microseconds. Military systems coordinate globally. Families separated by continents speak face-to-face. Knowledge spreads almost immediately. Human civilization became psychologically compressed. Distance began losing meaning. Space once resists that trend. Because the universe imposes a communication limit even more unforgiving than transportation limits, light speed. Nothing carrying information travels faster. This law changes everything once humanity leaves the solar system. Inside Earth's digital civilization, delays measured in milliseconds feel normal. Even satellite internet delays of hundreds of milliseconds are noticeable, but tolerable. Conversations remain fluid. Move outward. Earth-to-Moon communication delay is roughly 1.3 seconds each way. This already feels strange. Apollo astronauts experienced it. Mission control conversations carried slight pauses, not severe enough to prevent dialogue, but enough to remind everyone that distance had entered the conversation. Earth to Mars changes the experience dramatically. Depending on orbital positions, signal delay ranges from about 4 to 24 minutes one way. One way. Ask a question. Wait. Receive. Reply. A real-time conversation becomes impossible. This matters more than it first appears, because delays alter decision-making. Remote piloting becomes inefficient. Emergency intervention becomes impossible. Autonomy becomes necessary. Mars settlers, if they exist, will not be remote workers supervised from Earth. They will be operationally independent. Distance forces sovereignty. And Mars is close. Close by cosmic standards. The deeper implications emerge when we consider interstellar communication. A message sent to Proxima Centauri requires 4.24 years to arrive. A reply requires another 4.24 years. The fastest possible conversation takes nearly 9 years. 9 years for a single exchange. Imagine sending this message. Are you safe? Reply arrives almost a decade later. Yes. Communication at interstellar scale stops resembling conversation. It becomes correspondence across generations. Letters between civilizations. Archives, speaking to futures. This transforms governance immediately. Suppose humanity establishes a colony around Proxima. What political relationship can Earth maintain? Direct rule becomes absurd. Laws change faster than messages travel. Crises resolve before requests arrive. Leaders die between exchanges. Election cycles complete before replies return. Interstellar governance confronts a brutal reality. Centralized control fails. Distance enforces decentralization. This realization deeply influenced both futurists and political theorists. Many concluded that interstellar civilization cannot resemble modern nation-states or centralized empires. The communication lag is too severe. A galactic civilization, if it exists, may resemble something looser. Federations. Cultural lineages. Civilizational networks. Shared ancestry without synchronized governance. A family tree, not an empire. This is psychologically difficult because humans often equate expansion with unity. We imagine humanity spreading outward while remaining one coherent civilization. Physics disagrees. Light speed imposes historical drift. Separate worlds develop separate timelines. Separate timelines create separate cultures. Separate cultures create divergence. Eventually, human civilization may become a category rather than a single society. And there is something emotionally unsettling about this. Because communication delay does more than complicate politics. It changes relationships. Imagine leaving Earth for another star. Your parents remain behind. Your friends remain behind. Messages continue, but every exchange carries years of silence. Birth announcements arrive after children begin school. News of illness arrives too late to help. Deaths may be known years after funerals. Grief becomes asynchronous. Love becomes archival. This is one of the least discussed consequences of interstellar expansion. Emotional distance becomes physical law. Human psychology evolved for communities with rapid feedback. Social bonds depend on timely emotional exchange. Delayed communication strains intimacy. At cosmic scales, delay becomes permanent. And yet, communication remains essential, because isolated civilizations face another danger: knowledge loss. History teaches a painful lesson. Information preservation is fragile. Libraries burn, languages vanish. Archives decay. Oral traditions fracture. Civilizations repeatedly lose knowledge they assumed permanent. Digital civilization sometimes feels immortal, because storage is abundant. But storage is not permanence. Formats become obsolete. Hardware fails. Power grids collapse. Institutions disappear. Long-duration civilizations must actively preserve knowledge. This becomes existential in space. An isolated colony losing critical engineering knowledge could face catastrophic decline. A settlement dependent on complex life support systems cannot afford civilizational amnesia. Thus, communication becomes more than emotional support. It becomes redundancy, a safeguard against knowledge extinction. Shared archives across worlds could preserve civilization against local collapse. But even that raises new challenges. Bandwidth, transmission power, signal degradation. Interstellar communication requires extraordinary sensitivity. Signals weaken with distance. Noise accumulates. Detection becomes difficult. This problem fascinated astronomers involved in the search for extraterrestrial intelligence. If intelligent civilizations exist, why do we not hear them? One possible answer is simple. Distance destroys detectability. Signals weaken. Civilizations become quiet. The galaxy may not be empty. It may be disconnected. This possibility is haunting. Perhaps intelligence does emerge repeatedly across the galaxy. Perhaps civilizations build technologies, expand outward, send signals. And perhaps cosmic scale ensures that most remain effectively isolated, not alone. Separated. That distinction matters. Loneliness implies absence. Separation implies unreachable presence. The galaxy could contain countless civilizations hidden behind distance and time. Existing, thinking, building, unknown to one another, because communication itself cannot overcome scale. This brings us to a disturbing threshold. Until now, we have been thinking locally. One star, one nearby system, one interstellar conversation, but something much larger waits. Even if humanity solves travel, even if generation ships succeed, even if interstellar communication remains possible, we have barely begun confronting the true scale of our environment. Because the nearest stars are only local neighbours, the real structure surrounding us is far larger, far denser, far older. Hundreds of billions of stars. Our sun is not isolated. It belongs to something immense, a structure so vast that interstellar travel itself begins to feel small. The true challenge is no longer reaching another star. It is understanding the scale of the galaxy that contains them all. And once that scale becomes clear, the universe will feel larger again, much larger. By now, the scale of the challenge already feels immense. The moon shattered our intuition about nearby space. The solar system revealed that emptiness dominates local reality. The nearest star transformed interstellar travel into a civilization-scale problem. Communication delays showed that even successful expansion might fracture humanity into separate histories. And yet everything we have discussed so far exists inside a region that on cosmic scales is almost microscopic. Our sun is not alone. It belongs to a much larger structure, a galaxy. Specifically, the Milky Way. The word galaxy often fails to produce the emotional reaction it deserves, because modern culture uses the term casually. Phones advertisements, movies, software and product names have made the word familiar. Familiarity reduces awe, but the physical reality behind the word remains almost impossible to internalize. The Milky Way is not a cluster, not a neighborhood. not a cloud. It is a vast, gravitational civilization of stars, a rotating stellar metropolis, a structure so enormous that even after everything we have learned about interstellar distance, our previous scales now begin collapsing again. Start with stars. Astronomers estimate the Milky Way contains somewhere between 100 and 400 billion stars. Billion, not millions. Not merely hundreds of millions. Hundreds of billions. Even this number resists intuition. Suppose you counted one star every second. No sleep, no breaks. One star every second. Counting to 100 billion would take over 3,000 years. Longer than most recorded human civilizations. You could begin counting before the rise of ancient Rome and still not finish today. That is just the lower estimate. Numbers like this distort cognition because humans evolved for small communities. We intuit dozens, hundreds, perhaps thousands, with effort. Billions become abstractions. So once again, scale demands imagery. Imagine every star as a grain of sand, not a pebble, not a marble, a grain. Now gather 100 billion grains. You do not get a pile. You get landscapes, beaches, dunes, entire coastlines. And every grain represents a star, many with planets, some with moons, some with habitable zones, some perhaps with civilizations. Already the mind strains. Then comes distance. Because the Milky Way is not densely packed, this matters enormously. Science fiction often portrays galaxies as crowded starfields where stars seem visually close. Beautiful visuals, but misleading. In reality, stars are separated by immense emptiness. If our sun were the size of a tennis ball, nearby stars might still lie thousands of kilometers away. The galaxy contains many stars. It remains mostly empty. Again and again, the same truth returns. The universe is structured by islands and emptiness. Matter is the exception. Void is the rule. Now consider scale. The Milky Way spans roughly 100,000 light-years across. Some estimates push larger, depending on halo structure, but even conservative numbers are staggering. 100,000 light-years. Remember what a light-year represents. Light moving at the fastest speed allowed by physics takes 1 full year to travel that distance. To cross the galaxy from one side to the other, light itself requires roughly 100,000 years. Light, the cosmic speed champion, needs longer than all recorded human civilization just to cross our galaxy once. Pause there. This may be one of the most important psychological thresholds in astronomy. The galaxy is so large that even light experiences meaningful travel time. Not seconds, not minutes, not hours. Civilizational timescales. This transforms our understanding of observation itself. When we look across the Milky Way, we are not seeing the galaxy as it exists now. We are seeing historical layers. Nearby stars appear relatively current. Distant stars appear ancient. Light from the galactic center reaching Earth today began its journey roughly 26,000 years ago. When that light departed, humans had not built cities. Agriculture had not begun. No pyramids, no written language, no industrial civilization. Yet that ancient light arrives tonight. Observation becomes archaeology. The galaxy we see is partly past tense. This temporal layering creates extraordinary implications. Suppose a civilization existed 50,000 light-years away and observed Earth. They would not see modern humanity. They would see prehistory. Likewise, if we observed them, we might be seeing an ancient version of their world. Civilizations across galactic distances may never observe one another in synchronized time. Even coexistence becomes historically blurred. This deepens the communication problem beyond what Section 9 suggested. Interstellar communication across nearby stars was difficult. Galactic communication becomes almost mythological. A message crossing 10,000 light-years requires 10,000 years. A reply takes another 10,000. One exchange, 20,000 years. Empires rise and vanish inside that silence. Species evolve culturally. Languages disappear completely. Can such distances support civilization-wide identity? The answer grows increasingly bleak. Not because expansion is impossible, because coherence becomes improbable. This led thinkers to ask a profound question. What would a true galactic civilization even look like? Not a movie empire with centralized command. Physics forbids that. No emperor could rule effectively across millennia of signal delay. No parliament could legislate in meaningful real time. No military command structure could coordinate instantly. Galactic civilization would not behave like a nation. It would behave like evolution. Local adaptation, distributed autonomy, cultural branching, shared ancestry without shared present. This is difficult for human political imagination. We crave synchronized control. The galaxy rewards decentralization, and there is something even more unsettling. We are not in a privileged location. The Sun does not occupy the galactic center. It orbits far from it, roughly 26,000 light-years from the core, within one of the Milky Way's spiral arms. We are suburban, peripheral, ordinary. This matters philosophically. For much of history, humans placed themselves at centers. Earth centered the cosmos. The Sun later centered the solar system. But the galaxy offers no special placement. We are not central, not structurally, not geographically, not cosmically. Our star is one among billions orbiting a gravitational core dominated by something extraordinary. At the center of the Milky Way lies Sagittarius A star, a supermassive black hole containing roughly 4 million solar masses. Stars orbit it. Gas falls inward. Gravity shapes galactic architecture. Even here, scale becomes surreal. A black hole massive enough to influence the structure of an entire galaxy. And yet the galaxy itself is not the final scale. This is the next collapse of perspective. For centuries, humans believed the Milky Way might be the universe, a complete cosmic structure, the totality of creation. That belief felt reasonable. The galaxy already seemed incomprehensibly large. Surely nothing much larger existed. Then astronomers began noticing something strange. Faint cloudy structures in the night sky, spiral smudges, diffuse patches, nebulae they were called. For a long time, no one knew what they were. Gas clouds, star nurseries, nearby structures inside the Milky Way. The answer would permanently redefine scale, because the Milky Way was not the universe. It was only one galaxy, one among many. And once humanity realized that the size of the universe expanded so violently that even our galaxy began to feel small. For most of human history, the greatest obstacle to understanding the universe was not mathematics, it was depth perception. The night sky hides distance with almost cruel efficiency. Stars appear as points of light projected onto darkness, giving no obvious clues about how far away they truly are. Bright stars seem important. Faint stars seem distant. Yet even that intuition fails. A faint star may be relatively nearby but small. A bright star may be unimaginably distant, yet so luminous that it still dominates the sky. The heavens flatten themselves into illusion. To understand cosmic scale humanity, first had to solve a problem that sounds simple and becomes terrifyingly difficult the moment you attempt it. How do you measure distance to something you cannot touch? Something you cannot travel to? Something you cannot triangulate with ordinary human tools? This question haunted astronomers across centuries. Ancient sky watchers were extraordinary observers. Greek astronomers measured planetary motion with surprising precision. Islamic scholars refined astronomical tables and instruments. Renaissance scientists improved observational accuracy further. But despite all this progress, one truth remained elusive: distance. Without distance, the universe had no scale. Without scale, cosmology remained speculation. Then, one of the most elegant ideas in scientific history emerged: parallax. The concept sounds technical, but the experience is familiar. Hold a finger at arm's length. Close one eye. Then, switch eyes. Your finger appears to shift relative to the background. The finger did not move. You moved perspective. That apparent shift contains information. Distance. Nearby objects shift more. Distant objects shift less. Human vision uses this constantly. Astronomers realized Earth's orbit could become a giant measuring instrument. As Earth moves around the Sun, observers gain different viewpoints separated by millions of kilometers. Nearby stars should appear to shift slightly relative to distant background stars. That tiny shift reveals distance. In principle, elegant. In practice, brutal. Stars are so far away that the shifts are microscopic. For centuries, instruments lacked sufficient precision. Some critics even used the failure to detect parallax as evidence against heliocentrism. If Earth truly orbited the Sun, why could no stellar shift be observed? The answer was not that Earth stood still. The answer was that stars were far beyond contemporary imagination, much farther than anyone suspected. In 1838, a breakthrough arrived. Friedrich Bessel successfully measured the parallax of the star 61 Cygni. The shift was tiny, less than 1 arc second, an angle so small it is difficult to appreciate intuitively, yet that tiny motion changed everything. For the first time, humanity directly measured the distance to another star. The result was astonishing. The stars were not merely far, they were extraordinarily far. So far that Earth's entire orbit produced only a barely detectable positional shift. This measurement shattered lingering small universe intuitions. The stellar realm expanded dramatically, but parallax had limits. It worked for nearby stars. Beyond that, shifts became too small to detect. Humanity needed another method. Then another. And another. Thus emerged one of astronomy's most important intellectual structures, the cosmic distance ladder. The name matters. A ladder implies dependence. You cannot jump to the top. You climb rung by rung. Each rung depends on the previous one. This became essential because no single method measures all cosmic distances. Instead, astronomers built overlapping techniques. Nearby stars measured by parallax. More distant stars measured through brightness relationships. Galaxies measured through standard candles. Farther structures through redshift and cosmological expansion. Each rung extends reach. Each rung carries uncertainty. Each rung risks error propagation. If lower rungs are wrong, higher rungs inherit distortion. This made cosmic measurement one of the most delicate enterprises in science. Then came one of the most important characters in this story. Henrietta Swan Leavitt. In the early 20th century, working at Harvard College Observatory, Leavitt studied variable stars in the Magellanic Clouds. These stars changed brightness rhythmically, brightening and dimming over predictable periods. Many astronomers saw catalogues. Leavitt saw a pattern. She discovered that certain variable stars, known today as Cepheid variables, obeyed a remarkable relationship. The longer their brightness cycle, the more luminous they truly were. This changed astronomy profoundly. Why? Because apparent brightness alone tells little without knowing intrinsic brightness. A candle nearby and a lighthouse far away can appear similarly bright. But if you know an object's true luminosity, apparent brightness becomes a distance clue. Leavitt had found standard candles, cosmic light bulbs with predictable wattage. Measure the period. Infer true luminosity, compared to observed brightness. Calculate distance. Suddenly, the ladder gained a powerful new rung. Humanity could now estimate distances far beyond parallax reach. This breakthrough prepared the stage for one of the most consequential astronomers in history, Edwin Hubble. Working in the 1920s at Mount Wilson Observatory using the 100-inch Hooker telescope, Hubble examined faint spiral nebulae that had long puzzled astronomers. These fuzzy spirals were controversial. Some believed they were gas clouds within the Milky Way. Others suspected something far larger. The debate became known as the Great Debate in astronomy. Were spiral nebulae local or external? Hubble used Cepheid variables inside one of these spirals, the Andromeda Galaxy. He measured, calculated, compared. The result was revolutionary. Andromeda lay far beyond the Milky Way. Far beyond. It was not a nebula inside our galaxy. It was an entire galaxy, an island universe, a separate stellar metropolis. This single discovery triggered one of the most violent perspective collapses in intellectual history. The Milky Way stopped being the universe. It became one galaxy among many. Suddenly, the cosmic distance ladder extended outward into unimaginable scales. But success created a new problem. As astronomers measured farther and farther objects, something strange appeared. The universe itself was behaving unexpectedly. Distances were not enough anymore, because galaxies were not simply sitting still in static space. They were moving, and not randomly, systematically. The farther galaxies appeared, the faster they seemed to recede. This observation introduced a complication no one had fully anticipated. Distance itself was changing. Space was not a passive stage, it was dynamic, stretching, expanding. The ladder had measured the cosmos. Now the cosmos itself was beginning to move beneath the ladder, and that changed the meaning of distance forever. Once Edwin Hubble proved that the Andromeda Galaxy lay far beyond the Milky Way, the universe changed in a way that is difficult to overstate, not physically, psychologically. For centuries, humanity had repeatedly expanded its sense of scale. Earth lost its cosmic centrality. The solar system grew larger than ancient cosmologies imagined. The Milky Way then emerged as a vast stellar system containing hundreds of billions of stars. Each expansion felt transformative. Hubble's discovery was different. It did not merely enlarge the universe, it multiplied it. The Milky Way had seemed immense because it contained incomprehensible numbers of stars spread across enormous distances. But now astronomers were forced to accept something even more profound. The Milky Way was not unique, it was ordinary. One galaxy among many. This word ordinary carries enormous philosophical weight. Human history repeatedly resists ordinariness. Civilizations prefer centrality. Cultures construct stories of special placement. Even scientific revolutions that displaced Earth often left room for subtle anthropocentrism. Perhaps our star mattered. Perhaps our galaxy was special. The universe kept removing privilege. Our galaxy was not the cosmos. It was a member of a population, a single island in a vast archipelago of stars. The phrase island universe became deeply meaningful for early 20th century astronomers because it solved two problems at once. It acknowledged separateness and scale. Each galaxy was not merely a cloud of stars, but a self-contained gravitational civilization, a stellar continent, a cosmic city. A vast ecosystem of suns, planets, dust, gas, magnetic fields, radiation, and dark matter. And the distances between these islands were staggering. The nearest major galaxy, Andromeda, lies about 2.5 million light-years away. Pause on that number. When light now reaching Earth left Andromeda, early human ancestors had not yet emerged in modern form. No agriculture, no language families recognizable today, no cities, no civilization. That light began traveling before humanity became humanity, and tonight it arrives. This changes what seeing means. Astronomy is not merely observation, it is time travel through light. Every galaxy is both place and historical archive. Look farther. See older. This relationship between distance and time would become one of the most profound tools in cosmology. But first, astronomers had to grapple with scale. What is a galaxy really? At human scale, cities feel vast because they contain millions of people, infrastructure, and social complexity. Nations feel larger because they coordinate tens or hundreds of millions. Planets feel larger still because they contain entire biospheres. Galaxies transcend these analogies. A galaxy contains star systems the way a civilization contains households. The Milky Way alone may host hundreds of billions of stars, many with planets. If even a modest fraction host worlds capable of supporting life, then habitable environments could number in the billions. Billions. Inside one galaxy. And now multiplied by the number of galaxies, the mind strains. Astronomers soon discovered that galaxies themselves came in different forms. Spiral galaxies like the Milky Way and Andromeda. Elliptical galaxies massive and smooth, containing older stellar populations. Irregular galaxies, chaotic and asymmetric, often shaped by gravitational interactions. These structures were not static. Galaxies collided, merged, fed one another, distorted under gravity. This surprised many early astronomers because galaxies had initially been imagined as isolated systems, peacefully distributed through space. Reality proved more dynamic. Gravity operates across vast scales. Galaxies dance. Sometimes slowly, sometimes violently. Imagine two galaxies approaching over hundreds of millions of years. Stars rarely collide directly because interstellar distances are so immense. But gravitational interactions reshape entire stellar populations. Gas clouds compress. Star formation ignites. Spiral arms distort. Central black holes may eventually merge. Entire galactic architectures transform. Civilization-sized is no longer sufficient language. These are structure-sized processes unfolding across cosmic timescales. And one of those processes concerns us directly. The Milky Way and Andromeda are moving toward one another. Not away, toward. In roughly 4 to 5 billion years, the two galaxies are expected to collide and merge. The word collision sounds catastrophic, but remember the dominant truth of cosmic structure: emptiness. Stars are separated by enormous distances, so most individual systems may pass without direct impact. Yet gravitational restructuring will dramatically reshape both galaxies. The night sky of far future Earth, if Earth still exists, would become extraordinary. Andromeda would swell from faint smudge to colossal luminous structure spanning much of the sky. Two island universes merging, two stellar civilizations of matter becoming one larger system. Even here, scale continues escalating. Galaxies seemed like final units. They were not. Astronomers began observing clusters, groups of galaxies bound by gravity. Then, superclusters, even larger structures containing clusters and filaments of galaxies. The architecture kept expanding. Again and again, each boundary dissolved into larger organization. Human intuition repeatedly searched for endpoints. The universe repeatedly denied them. This is what makes cosmic scale psychologically exhausting. There is no comfortable stopping point. Every scale becomes local when viewed from a larger one. Star systems become neighborhoods inside galaxies. Galaxies become units inside clusters. Clusters become nodes inside larger structures. Perspective keeps receding. But while astronomers mapped more galaxies, another puzzle emerged. Distances alone were not enough. Motion mattered. This is where Hubble returned to center stage. Using galaxy observations, he noticed something remarkable. Light from many distant galaxies appeared shifted toward longer wavelengths, redder. This phenomenon, redshift, implied recession. Galaxies were moving away, but not randomly. A pattern emerged. The farther a galaxy appeared, the faster it receded. This relationship became one of the most consequential discoveries in modern science, because it implied something extraordinary. The galaxies were not simply moving through space like shrapnel from an explosion. Space itself was changing, stretching, growing, expanding. This distinction matters profoundly. Imagine dots drawn on a balloon. As the balloon inflates, each dot sees every other dot moving away. The dots themselves need not actively travel across the surface. The surface expands. That analogy, imperfect but useful, captures a terrifying realization. The universe is not static. The stage itself moves. Distance is not fixed. It grows. And this changes everything we thought distance meant. Until now, we treated cosmic distance as difficult but stable. A destination far away remains far away. Travel longer, arrive eventually. Expansion introduces something more unsettling. Destinations may recede while you travel. Space can stretch between origin and destination. The universe was no longer merely large. It was becoming larger, continuously. That realization transformed cosmology. It also introduced one of the deepest questions humanity has ever faced. If the universe is expanding now, what does that say about its past? And what does it imply about its future? The answer would take us beyond galaxies entirely, beyond clusters, beyond visible structure, into the dynamic architecture of space-time itself. And there, distance would stop being a fixed measurement. It would become history in motion. The discovery that galaxies were receding from one another did not merely add another fact to astronomy. It changed the foundation of cosmology. Until the early 20th century, many physicists assumed the universe was static on large scales. Stars might move, galaxies might rotate, local structures might evolve, but the universe itself, the grand stage containing everything, was often imagined as eternal and unchanging, stable, permanent, a cosmic backdrop against which history unfolded. Then the measurements refused to cooperate. When Edwin Hubble compared galaxy distances with their redshifts, the pattern became increasingly difficult to ignore. Distant galaxies were moving away faster than nearby ones. The relationship was systematic. Distance and recession were linked. This observation became known as Hubble's law. At first glance, it can sound deceptively simple. Farther galaxies recede faster. But hidden inside that sentence lies one of the strangest truths in science. The universe expands everywhere. This point matters because human intuition immediately asks a misleading question. What is the universe expanding into? It is a natural question. It is also the wrong one. Expansion does not mean galaxies are flying outward into pre-existing empty space, like debris from a conventional explosion. That image fails because it assumes space exists as a fixed container. General relativity suggested something stranger. Space itself changes. Distances between gravitationally unbound structures increase because space-time stretches. The container expands. This is extraordinarily difficult to internalize because nothing in ordinary life behaves this way. Houses do not expand while furniture moves apart. Cities do not stretch continuously between buildings. Human perception evolved in environments where spatial geometry is effectively stable. Cosmology violates that intuition. To visualize expansion, imagine standing inside an infinite grid painted on elastic fabric. Every square slowly grows. Every point sees distant points moving away. No special center is required. From every location, everything distant recedes. That is what the large-scale universe resembles. No privileged center, no cosmic middle, No preferred edge. Every observer sees expansion. This realization delivered another philosophical blow to human centrality. Not only are we not at the center of the solar system, not only are we not at the center of the galaxy, we are not at the center of the expanding universe either. There is no special observational throne. Every sufficiently large-scale observer sees the same broad pattern. The universe democratized perspective. This was beautiful. It was also unsettling, because once astronomers accepted expansion, a terrifying implication followed naturally. Run the expansion backward. If distances grow today, then in the past they were smaller. Farther back, smaller still. Continue backward far enough, and all large-scale structure compresses into a dramatically denser state. Galaxies approach. Matter compresses. Temperatures rise. Density climbs. Eventually, the observable universe reaches conditions so extreme that familiar structures cease to exist. No galaxies, no stars, no atoms, no chemistry, only an ultra-hot early cosmos. This became the foundation of what we now call the Big Bang model. The phrase is culturally famous, yet often misunderstood. It does not describe an explosion in space. It describes rapid expansion of space from an extremely hot, dense early state. That distinction matters, because if space itself expanded, then the Big Bang was not something that happened at one location. It happened everywhere. Every region of the observable universe traces backward toward that early state. This realization transformed cosmic distance into something even more profound. Distance became time. Look farther, see earlier. Astronomy became history. The farther we observe, the deeper into cosmic past we travel. This relationship created one of the most intellectually rewarding ideas in modern science. Telescopes are time machines. Not metaphorically, physically. Because light takes time to travel. The night sky is layered history. Look at the moon, you see it 1.3 seconds ago. The sun, 8 minutes ago. Jupiter, tens of minutes ago. Nearby stars, years ago. Distant galaxies, millions or billions of years ago. The deeper we observe, the younger the universe appears. This means cosmic scale is inseparable from cosmic history. Large distance is ancient time. That equivalence is extraordinary. Yet expansion introduced another complication. The universe was not expanding through empty nothingness without consequence. Expansion affects light itself. As space stretches, wavelengths stretch with it. Light traveling through expanding space becomes redshifted. Its wavelength lengthens, energy decreases. Photons lose energy not because they slow, but because the geometry they traverse evolves. This effect became one of astronomy's most powerful tools. Measure redshift. Estimate recession. Infer cosmic distance and age. Suddenly astronomers could map not merely static positions, but dynamic history. The universe became measurable across immense scales. But as precision improved, something surprising emerged. Expansion was not behaving exactly as expected. For a long time, cosmologists assumed gravity should gradually slow expansion. Matter attracts matter. Galaxies pull on galaxies. Large-scale structure should resist outward motion. Expansion should decelerate. That seemed reasonable. Then, late 20th century observations delivered a profound surprise. Expansion was not slowing as expected. It was accelerating. This was deeply disturbing, because it implied something enormous and poorly understood dominated cosmic behavior. Some unknown influence was driving large-scale expansion faster over time. Astronomers gave it a cautious name: dark energy. The name sounds explanatory. It is mostly descriptive. It means we observe accelerated expansion caused by something not yet understood, and the scale involved is extraordinary. Dark energy appears to dominate the energy budget of the universe. Ordinary matter, everything visible, stars, planets, gas, dust, and people, represents only a small fraction of cosmic content. A small fraction. This realization created yet another collapse of perspective. Humanity had spent centuries measuring visible structure. Now evidence suggested most of cosmic reality was invisible and poorly understood. The universe became larger, not just spatially, but conceptually. Unknowns expanded, and with acceleration came an unsettling question. What happens if expansion continues forever? The answer leads to one of the most disturbing implications in cosmology. Because accelerated expansion does more than enlarge the universe, it changes accessibility. Galaxies recede faster over time. Some structures remain gravitationally bound, others drift beyond causal reach, and once certain thresholds are crossed, no technology can recover them. Not because engineering fails, because space-time itself removes them. This brings us to one of the most sobering truths in modern cosmology. Some parts of the universe are already beyond humanity's future reach, forever. Distance once merely difficult is becoming final, and that changes the meaning of cosmic possibility itself. There is a subtle comfort hidden inside most discussions of space. Even when distances feel overwhelming, people often preserve an unspoken assumption. Given enough time, given enough technology, given enough energy, anything can eventually be reached. That assumption has followed humanity for centuries. Mountains once thought uncrossable were crossed. Oceans once feared as boundaries became trade routes. Continents separated by vast waters became connected by ships, aircraft, and digital networks. History repeatedly rewarded persistence, so we internalized a powerful belief. Distance is temporary. Distance yields to progress. The expanding universe challenges that belief at its foundation, because there exists a kind of distance that technology cannot defeat. Not difficult distance, final distance. This is where cosmology becomes emotionally unsettling. Until now, every obstacle in our story still allowed some version of hope. The moon was far, but reachable. The planets were separated by immense emptiness, but probes crossed that emptiness. Nearby stars demanded civilization-scale engineering, but physics did not completely forbid the journey. Even galaxies, though staggeringly distant, remained conceptually locatable. Expansion changes the rules. Because space itself is not passively sitting still while civilizations plan voyages, it stretches continuously, and in some cases it stretches fast enough that destinations recede beyond all future reach. This is one of the most profound consequences of accelerated expansion. There are galaxies we can see today that we can never visit, ever. Not with better rockets, not with fusion drives, not with relativistic ships, not with technologies we have not yet imagined, so long as they obey known physics. The barrier is not engineering, it is causality. To understand this, imagine walking up a downward moving escalator. If you climb faster than the escalator descends, you gain progress. If both speeds match, you remain fixed. If the escalator moves downward faster than you can climb, no effort reaches the top. Expansion creates an analogous problem. For sufficiently distant galaxies, the stretching of space between us and them effectively outpaces any possible future attempt to close the gap at subluminal speeds. Light itself becomes the reference. If space-time expansion prevents even light emitted now from ever reaching certain destinations in useful ways, practical access disappears. This leads to a concept both beautiful and haunting: the cosmic event horizon. The word horizon is important. Horizons are psychologically powerful because they imply visibility without access. You can see a horizon, but moving toward it does not guarantee arrival. It marks a boundary between reachable and unreachable regions. The cosmic horizon serves a similar role. It defines a boundary beyond which events can no longer influence us in the future, not because those regions cease to exist, because expansion severs causal connection. This distinction matters. Those galaxies remain real. Stars still form there. Planets still orbit. Perhaps civilizations rise and fall, but their future becomes permanently disconnected from ours. The universe contains realities forever inaccessible. That idea is profoundly difficult for the human mind because it violates a deep instinct. We equate visibility with possibility. If we can see something, we assume it exists within eventual reach. Cosmology says otherwise. Seeing does not imply access. You can observe light from regions whose future is forever lost to you. That sentence deserves pause. Light arriving today may come from a galaxy whose current state can never be known directly. We receive ancient photons. The future of that galaxy remains unreachable. This transforms astronomy into something strangely bittersweet. Observation becomes contact with historical ghosts. We do not simply observe distant objects. We observe versions of them from earlier cosmic eras. Their present may already lie beyond causal reach. This means the observable universe and the reachable universe are not identical. This distinction often surprises people. The observable universe contains everything whose light has had time to reach us since the early universe became transparent. But the reachable universe is smaller, much smaller. There are regions we can observe, but never influence. This realization carries extraordinary philosophical weight. For thousands of years, human exploration expanded accessible territory. New land meant new resources, new cultures, new futures. Discovery implied possibility. Cosmology breaks that link. Discovery no longer guarantees access. Knowledge can exceed agency. We may know something exists, while knowing it can never become part of our future. This is a deeply modern form of limitation, and the implications stretch far beyond travel. Consider the long-term future of civilization. Suppose humanity survives for millions, even billions of years. Suppose technology becomes astonishingly advanced. Suppose interstellar expansion succeeds across local regions of the galaxy. Even then, cosmic acceleration continues. Over immense timescales, more galaxies drift beyond reach. The visible universe slowly empties, not immediately, not dramatically on human timescales, but inexorably. Far future astronomers in gravitationally bound systems may see fewer and fewer external galaxies. Cosmic expansion will gradually erase visible evidence of the broader universe. This leads to a remarkable thought experiment. Future civilizations may know less about cosmology than we do, not because they are less intelligent, because evidence disappears. Right now, humanity lives during a scientifically privileged era. We can still observe cosmic expansion. We can still detect distant galaxies. We can still infer early universe history through structures visible across vast distances. Billions of years from now, much of that evidence may be inaccessible to observers inside isolated galactic remnants. This is extraordinary. It means cosmic understanding depends partly on timing. Civilizations born at different cosmic epochs inherit different observational universes. The universe is not only spatially structured, it is epistemically structured. Knowledge itself depends on when you exist. This adds another layer to our central question: how big is the universe? The answer now depends not only on distance, but on access, observation, and time. Size becomes contextual. The universe may be vastly larger than what any civilization can ever observe. That possibility changes everything, because once we accept that the observable universe may be only a fraction of total reality, a deeper mystery emerges. What lies beyond observation, beyond the cosmic horizon, beyond the furthest light that can ever reach us? For most of our journey tonight, scale expanded through measurement. Now measurement begins failing. The ladder ends. Observation reaches a boundary. And at that boundary, modern cosmology confronts one of its greatest discoveries. The universe we can see may not be the universe that exists. What lies beyond may be far larger than everything we have discussed so far. Much larger than galaxies. Much larger than clusters. Possibly far larger than the observable universe itself. And this is where the story turns. Because after 14 sections of escalation, humanity finally reaches the threshold of a breakthrough. Not a technological breakthrough, a conceptual one. A new way of seeing the architecture of everything. For centuries, astronomers believed the universe might be broadly uniform on the largest scales, galaxies scattered through space like distant islands in an ocean of darkness. Perhaps slightly clustered, perhaps gently uneven, but fundamentally simple. That intuition collapsed, slowly, then suddenly. As surveys expanded and telescopes grew more sensitive, astronomers began charting not just individual galaxies, but their relationships. And what emerged was not random distribution. It was structure. Gigantic structure. When mapped across hundreds of millions of light years, galaxies did not appear evenly spread. They formed patterns, chains, walls, filaments, voids. Space itself began to resemble something unexpected, a web. Not a uniform void filled with isolated galaxies, but a vast, interconnected architecture where matter gathers along invisible threads. This is the cosmic web, and it represents one of the most important realizations in modern cosmology, because it reveals that even at scales where gravity seems weak and emptiness dominates, structure still emerges. Galaxies are not merely scattered objects. They are nodes in a larger network. Along filaments, galaxies cluster and grow. At intersections, massive structures form regions where gravitational attraction has concentrated matter over billions of years. Between these filaments lie enormous voids, regions of near emptiness where few galaxies exist. These voids are not small gaps, they are immense. Some span hundreds of millions of light years, with only sparse traces of matter. Imagine travelling through such a void. For millions of years you would see almost nothing. No nearby galaxies, no bright structures, only faint distant light at the edges of perception. Even emptiness has structure at cosmic scale. This realization changed how scientists think about formation. The universe is not a uniform expansion of matter. It is a process of gravitational sculpting. Over time, small fluctuations in the early universe grew into the structures we observe today. Slightly denser regions attracted more matter. Those regions grew denser still. Over billions of years, this feedback created a network of filaments stretching across space. And inside this web, galaxies evolved, clusters formed, superclusters emerged, enormous structures connected across unimaginable distances. One of the most famous is the Laniakea supercluster. Its name, drawn from Hawaiian meaning immense heaven, reflects the scale involved. Laniakea contains tens of thousands of galaxies, including our own Milky Way. For the first time, astronomers were forced to redefine cosmic location again. We are not merely in a galaxy. We are in a supercluster, a gravitational region so large that its boundaries are defined not by visible edges, but by motion. Galaxies within it flow together under mutual gravity. And yet even this is not the largest structure. Beyond superclusters lie even more complex arrangements. Filaments connecting clusters across hundreds of millions of light years, enormous voids separating them, a patchwork of matter shaped by both gravity and the early conditions of the universe. But the most important implication of the cosmic web is not its beauty, it is its fragility. Because structure at this scale is delicate. It depends on subtle balances of gravity expansion and time. Slight changes in early conditions would produce entirely different cosmic architectures. A slightly denser universe might collapse into fewer, larger structures. A slightly less dense one might produce a sparse scattering of galaxies. Our universe sits in a narrow regime where complexity is possible. This raises a deeper question. Why does structure exist at all? Why is the universe not simply smooth and uniform? The answer lies in tiny fluctuations present in the early universe. Minute variations in density, smaller than anything directly visible, seeded the entire cosmic structure we now observe. These fluctuations were not random noise in a trivial sense. They were the origin of everything structured. Without them, there would be no galaxies, no stars, no planets, no observers. This means that the largest structures in the universe trace their origin to the smallest variations in its earliest moments. Scale collapses into itself. And yet, even as we map this vast architecture, another realization emerges. The cosmic web is not static. It evolves. Galaxies move along filaments, clusters merge, voids expand. Gravity continues to reshape structure over time. But all of this happens within a larger context: expansion. The same expansion that revealed distant galaxies are receding also influences the long-term fate of cosmic structure. Over immense timescales, expansion competes with gravity. Inside clusters and superclusters, gravity holds structures together. Between them, expansion pulls them apart. And in regions where expansion dominates, structure gradually becomes inaccessible. This leads us back to a central tension. The universe is both connected and separating. At one level, it is a web of gravitational relationships. At another level, it is a space stretching everything apart. These two forces coexist, but they do not balance equally everywhere. Some regions remain bound, others drift away forever. This creates a future where the cosmic web does not simply exist, it evolves into isolation. Over billions of years, distant filaments will fade from observable reach. Entire clusters will slip beyond horizons. The universe will appear less structured from any given location. Future observers trapped within gravitationally bound remnants may see only their local cluster of galaxies. The rest of the cosmic web will have vanished beyond the horizon of causality. In a profound sense, structure itself is temporary. Even the most magnificent cosmic architecture is not permanent. This raises a deeper question that now becomes unavoidable. If structure fades over time, if distance grows between even the largest systems, if observation becomes increasingly limited, then what exactly defines the true size of the universe? Is it what we can map, what we can observe, what we can reach, or something far beyond all three? Because every new discovery so far has expanded the universe outward. First planets, then stars, then galaxies, then superclusters, then the cosmic web itself. Each layer revealed something larger underneath. But now we are approaching a boundary where structure no longer guarantees access. And beyond that boundary lies the most fundamental horizon of all, the edge of everything that can ever be seen. The universe is about to stop being a structure we map and become a limit we encounter. There is a boundary in the universe that does not look like a boundary. No wall, no edge, no sudden change in texture or darkness. From any direction you choose, the sky looks continuous. Stars fade into galaxies, galaxies fade into faint smudges, and beyond them, darkness stretches uniformly in every direction. Yet hidden inside that uniformity is a hard limit, not of matter, but of information. This is the observable horizon. It is the farthest distance from which light has had time to reach us since the early universe became transparent. Beyond it, there are regions of space that exist, but whose light has not yet arrived here, and in some cases, never will. This is not a limitation of telescopes, it is a limitation of time. To understand it, we return once more to the simplest truth in cosmology. Light has a speed, and the universe has an age. Those two facts combine into a profound consequence. We can only see as far as light has had time to travel. Everything beyond that limit is hidden, not by obstruction, but by delay. So when we observe the deepest regions of the sky, we are not seeing far away in the ordinary sense. We are seeing back in time. The universe is not only spatially large, it is temporally deep. The cosmic horizon is therefore not just a distance marker, it is a historical boundary. When we look toward the edge of the observable universe, we are looking toward the earliest eras of cosmic structure. Galaxies in their infancy, matter still organizing, light stretching across expanding space for billions of years before reaching us. At the extreme limits, we encounter radiation from a time when the universe was dramatically different. Hot, dense, opaque, before stars existed, before galaxies formed, before structure as we understand it emerged. This is where observational cosmology reaches its deepest window. But even this window has limits. Because the universe itself is evolving in a way that slowly redraws what can be seen, expansion does not merely stretch space, it changes what light can reach us in the future. This leads to a distinction that is subtle but critical. The observable universe is not fixed. It grows over time as light from more distant regions finally arrives. But simultaneously, expansion can push other regions beyond the horizon of future visibility. So two processes occur at once. New light arrives, and old regions disappear from future reach. The universe is both revealing and concealing itself. This dual motion creates a paradoxical experience for any civilization over long timescales. The sky does not remain constant. It changes in content. Over extremely long periods, distant galaxies will fade, not because they vanish, but because their light will no longer be able to reach observers. Cosmic acceleration stretches space faster than light can traverse it over certain distances, effectively isolating regions of the universe from one another. This is where the concept of a cosmic event horizon becomes unavoidable. Unlike the horizon of a planet, which is defined by curvature and line of sight, the cosmic horizon is defined by expansion and time. It marks the boundary beyond which events can never influence us in the future, not because they are too far right now, but because the geometry of space-time ensures that light emitted there even now will never reach us. This is a profound shift in thinking. In everyday life, distance is a challenge of effort. In cosmology, distance becomes a question of possibility. Some regions are not merely far, they are permanently disconnected, even if they exist, even if they are luminous, even if they are filled with galaxies, stars, and perhaps civilizations. They are, in a very real sense, outside our future. This leads to an unsettling realization. The universe is larger than what can ever be known, not just larger than what we have explored, not just larger than what we can currently observe, but larger than what any future observation, no matter how advanced, can ever reveal. And yet we still attempt to map it. Using the faint light that reaches us, astronomers reconstruct the geometry of cosmic expansion, measure its rate, and estimate the size of the observable universe. That size is already immense, roughly 93 billion light-years across in diameter, accounting for expansion since the early universe. But even that number is often misunderstood. It is not the size of the universe. It is the size of what we can see, a window, not the whole structure. This distinction is essential, because when we say the universe is 93 billion light-years wide, we are describing perception, not totality. The true universe may be vastly larger, possibly infinite, possibly finite, but unbounded, possibly structured in ways that extend far beyond causal reach. We do not yet know, and perhaps we cannot know. This is where cosmology reaches its philosophical edge. Science, which began by expanding knowledge, now encounters limits defined by the universe itself. Not technological limits, not methodological limits, fundamental limits. The horizon is not moving because we are slow. It is moving because space-time is structured that way. This creates a strange situation for intelligence within the universe. We are capable of understanding that there is more than we can observe. We can calculate regions we will never access. We can infer structures we will never directly confirm. We can describe a universe that is partially forever hidden. In a sense, the universe has become larger than observation allows comprehension to complete. And yet, even within this limitation, something remarkable persists. The portion we can see is not random. It is structured, coherent, mathematically describable. The cosmic horizon does not separate us from chaos. It separates us from additional order we may never witness. So the question becomes sharper. If the observable universe is only a fragment, what does that say about the rest? Is it similar? Is it different? Does it follow the same laws? Or does reality extend into regimes that are fundamentally inaccessible, not just in distance, but in principle? At this point, distance stops being a measurement. It becomes a philosophical boundary between knowledge and existence. We have reached the edge of observation, but not the edge of possibility, because beyond the observable horizon lies a question that science can frame, but not yet answer. And that question forces us to confront the final layer of scale. Not galaxies, not clusters, not even the observable universe, but everything that exists beyond what can ever be seen, and whether size has any meaning there at all. There is a moment in every attempt to understand the universe when measurement stops feeling like discovery and starts feeling like limitation. We build instruments to see farther. We refine equations to describe deeper structures. We extend observation across billions of years of cosmic history, and then quietly, the universe draws a boundary that is not marked by anything visible, only by consequence. Beyond the observable horizon, there may exist regions of space that are real in every physical sense, yet permanently disconnected from us. Not hidden, not obscured, disconnected. This distinction is critical because it changes what unknown means. Unknown usually implies eventual knowability, a mountain not yet climbed, a continent not yet reached, a star not yet visited. But cosmology introduces a different category, unknown, that can never become known, not due to lack of effort, but due to the structure of space-time itself. At this point, the universe ceases to behave like a map we are gradually filling in, and begins to resemble something far more unsettling. A partially accessible reality. A cosmos where knowledge is bounded not by intelligence but by causality. The observable universe, vast as it is, contains everything whose light has had time to reach us since the universe became transparent. But beyond that lies a larger whole whose properties we can only infer indirectly, if at all. We are like observers inside a fog bank, reconstructing the shape of an ocean we cannot fully see, based only on waves that reach our position. And yet those waves are consistent, predictable, mathematically structured. This is where modern cosmology becomes extraordinary. Even though we cannot see beyond the horizon, the portion we can see behaves as though it is part of a larger, coherent system governed by uniform physical laws. Gravity behaves consistently. Light behaves consistently. Expansion behaves consistently. Time behaves consistently. This consistency allows us to infer that the unseen universe is not arbitrary. It likely follows the same rules, but inference is not access. And here lies the tension. We can describe a reality that extends beyond observation. We can model it mathematically. We can simulate its possible structure, but we cannot confirm its full extent. This raises a question that has no simple scientific resolution. If a region of the universe cannot be observed, influenced, or interacted with in any way, does it belong to our physical understanding in the same way as observable reality? Science by its nature depends on observation, but cosmology pushes observation to its limit and beyond. At the edge of the observable universe, we encounter a boundary where physical theory continues, but empirical access ends. This does not invalidate science. It defines its frontier, and that frontier is not a place. It is a horizon in time and space. Beyond it there may be galaxies forming, stars igniting, and structures evolving in ways identical to what we observe locally. Or there may be differences we cannot detect. Entire regions of reality evolving independently, forever separated from causal contact. We cannot currently distinguish between these possibilities. This uncertainty is not a failure of science. It is a consequence of scale. As we move outward in cosmic distance, we begin to see a pattern repeated at every level of this journey. Earth once seemed large and complete. The solar system revealed emptiness beyond expectation. The nearest stars exposed interstellar distance as overwhelming. The galaxy transformed our understanding of structure entirely, and now the observable universe itself becomes only a fraction of a potentially much larger whole. At every step, what we thought was the universe became a smaller part of something greater. This recursive expansion of perspective suggests a deeper truth. The universe does not simply grow in size as we explore it. It grows in conceptual depth. Each boundary is not an endpoint, but a threshold into a larger framework. And yet, beyond the observable horizon, we encounter something new. Not just unknown structure, but unknown accessibility. Because even if the universe beyond is infinite, or vastly larger than what we can observe, it may remain forever disconnected from us. This creates a profound asymmetry in knowledge. We can know that something exists. We can infer its properties. We can include it in equations, but we may never interact with it, never observe it directly, never confirm its details. This is a new kind of epistemological boundary, not ignorance, but separation. At this point, cosmology intersects with philosophy in a deeply uncomfortable way. Because the universe no longer behaves like a system we are embedded in fully, it behaves like a system we are partially excluded from. And yet, even within this limitation, something remarkable persists. The observable universe is not chaotic. It is structured in a way that allows comprehension. Galaxies form predictable distributions. Expansion follows measurable laws. Light carries consistent information. This suggests that even if the universe extends far beyond what we can see, the part we inhabit is not arbitrary. It is representative, or at least consistent with a larger order. But consistency is not completeness. We are left with a universe that is simultaneously comprehensible and unreachable in its totality. And that duality leads us to a final realization about scale itself. Perhaps size is not a property that applies uniformly that exists. Perhaps size is meaningful only within the region of the universe that is causally connected. Beyond that, the concept may lose definition entirely. Because measurement requires interaction, and interaction requires connection. Without connection, there is no measurement, only inference. And inference, no matter how powerful, is not the same as contact. So we arrive at a strange conclusion. The universe may be larger than anything we can ever observe, but it is also larger than anything we can ever verify. And that gap between observation and reality becomes one of the defining features of modern cosmology. Not a failure to know, but a boundary of knowing itself. This is where our journey reaches its most abstract point, because the next question is no longer about what lies beyond the observable universe. It is about whether the universe in its totality has a size at all that human concepts can meaningfully capture, or whether we are attempting to measure something that is fundamentally beyond the idea of measurement. And that question leads us into the final layer of scale, where the universe is no longer just expanding, but confronting the limits of what size can even mean. At this point in our journey, every familiar anchor of understanding has begun to dissolve. We started with Earth, a world that felt vast to its inhabitants. We expanded to the Moon, then the solar system, then interstellar space, then the galaxy, then the cosmic web, then the observable universe itself. At each step, the universe expanded not just in distance, but in conceptual resistance. And now we arrive at the most uncomfortable question of all. What is the universe in totality? Not what can we see, not what we can reach, not even what we can infer, but what exists regardless of observation. Cosmology offers several possibilities, each more unsettling than the last. The first is the simplest to state and the hardest to visualize. The universe may be infinite. An infinite universe does not mean merely very large. It does not mean billions or trillions of light years across. It means no boundary exists at all. No edge, no final galaxy, no ultimate horizon where structure ends. Space would extend without limit in every direction. Galaxies would continue without end. Stars would repeat in patterns across scales so vast that duplication of structure becomes statistically inevitable. In an infinite cosmos, anything that is physically possible is not just possible somewhere. It is inevitable somewhere. There would be regions so distant that light from them will never reach us, not because of expansion alone, but because there is simply no end toward which it could converge. Infinity removes the concept of far away as a final category. Everything becomes somewhere within an unbounded structure. But infinity is not the only possibility. There is another, more subtle idea. The universe may be finite, yet unbounded. This sounds contradictory, but it emerges naturally from certain geometries of space-time. Consider the surface of Earth. It has finite area, yet you can walk in any direction without ever encountering an edge. You do not fall off. You do not reach a boundary. You simply continue, eventually returning to where you started, if you travel long enough. Now imagine that principle extended into higher dimensions. Space itself could be shaped in such a way that it is finite in total volume, but contains no edges, no boundary, no outer wall, no beyond, only continuous curvature. In such a universe, travelling far enough in one direction might eventually bring you back to your starting region, though the scale required would be far beyond any conceivable journey. This idea removes infinity while preserving completeness, but it introduces a different kind of strangeness, because if the universe is finite but unbounded, then size becomes absolute again, but still inaccessible. There is a total amount of space, yet no observer can ever experience its full extent. And then there is a third possibility, one that modern physics increasingly takes seriously in theoretical frameworks. The universe may be far larger than the observable region, but structured in ways we cannot directly access, possibly infinite in some dimensions, possibly finite in others, possibly shaped by physics operating at scales we cannot probe. In some models, what we call the universe may be only one region within a much larger multiversal structure, where different regions obey different physical conditions. These ideas remain speculative, but they emerge naturally from attempts to unify cosmology and quantum physics, and they highlight a deeper truth. The more precisely we define the universe, the more possibilities appear. This creates a paradox at the heart of cosmic understanding. We are not approaching a single answer. We are approaching a space of possible answers. And each possibility reshapes the meaning of size itself, because size depends on comparison. We measure distances relative to something else. We define edges relative to boundaries. We understand scale through containment. But if there is no external reference frame, no outer context, no boundary beyond which comparison is possible, then size becomes a concept embedded inside the universe, not applied to it from outside. This is where human intuition begins to fail in a fundamental way. We instinctively imagine the universe as an object within a larger emptiness, but cosmology suggests there is no larger emptiness, no external container, no outside perspective, only the universe itself. This removes the observer's privilege of standing outside what is being measured. We are always inside, always embedded, always part of what we attempt to describe. And so the question, how big is the universe, begins to shift. It is no longer purely a question of measurement. It becomes a question of meaning, because even if the universe is infinite or finite but unbounded or structured beyond observable reach, we are still confined to a single perspective within it. That perspective defines what size even means for us. And yet, despite these limitations, humanity has managed something extraordinary. We have constructed a coherent description of a cosmos that extends far beyond direct experience. We have mapped galaxies we will never reach, inferred structures we will never observe, described epochs of time we will never witness, and built a narrative of reality that stretches to the limits of causality itself. This is perhaps the most remarkable achievement of cosmic science. Not that we discovered everything, but that we discovered how far everything might extend beyond us. And still, the question remains open, not because we failed to answer it, but because the answer itself may not be a single number, or a single structure, or even a single scale. It may be a landscape of possibilities. And in that landscape, the universe is not simply big, it is unbounded in the deepest sense, either infinitely extended, or finitely complete without edges, or structured in ways that make outside an undefined concept. At this point, size stops behaving like a measurement, and starts behaving like a reflection of our own limitations. We are not just asking how large the universe is, we are asking how large reality can be, while still being comprehensible from within it. And that question has no final horizon, only deeper layers of perspective, each one expanding the previous, each one dissolving certainty into something larger. And so we arrive at a final realization in this section of our journey. The universe may not be something we stand outside and measure. It may be something we are perpetually embedded within, forever expanding in understanding, but never in position. And in that sense, its true size is not just physical, it is experiential, defined not only by what exists, but by what can ever be known from where we are. At this stage of the journey, something subtle has changed. We are no longer asking where things are. We are no longer asking how far they are. We are no longer even asking what exists beyond them. We are asking what it means to exist inside something so vast that it resists completion. Because once the universe expands beyond galaxies, beyond the observable horizon, beyond even the boundaries of conceptual infinity, distance stops being the main problem. Meaning becomes the problem. Civilization is not built on scale alone. It is built on interpretation. A species can survive in a small valley, a continent, a planet, even a solar system, as long as it can organize meaningfully around its environment. Meaning provides structure to time. It connects individuals to collective purpose. It binds generations into continuity. But as the universe grows in scale, meaning begins to face pressure. Not from contradiction, from dilution. Consider what it means for a civilization to understand that it occupies only one small region of a galaxy like the Milky Way. Hundreds of billions of stars exist beyond any practical reach. Entire regions of chemical and gravitational complexity unfold without interaction with us. Now extend that realization further. Galaxies beyond the Milky Way, each with their own histories, structures, and possibly life-bearing systems, expanding away through cosmic time. Now extend it again. A universe where even those galaxies represent only a fraction of total existence. At each step, humanity's relative position shrinks, not physically, existentially. This shrinking does not diminish importance in a scientific sense. A single human life still contains complexity, consciousness, and agency. A single civilization still generates knowledge, culture, and transformation. But the background against which that meaning is interpreted grows continuously. This creates a tension that has no historical precedent. On Earth, meaning was anchored in immediate environment. Survival, community, territory, and continuity provided stable reference points. Even when societies expanded, they did so within a shared planetary context. Cosmic scale removes that shared boundary. When we learn that the observable universe extends over tens of billions of light years, and potentially far beyond, we are forced to reinterpret the significance of local events against an almost incomprehensibly large backdrop. A question emerges that is not scientific in nature but civilizational. Does meaning scale with size, or does it remain local? If the universe is vast beyond comprehension, does that make individual existence smaller, or does it simply relocate meaning into a different framework? One possibility is that meaning is independent of scale, that consciousness, experience, and understanding retain full significance regardless of cosmic context. In this view, the universe's vastness does not diminish importance, it only reframes it. Another possibility is more unsettling. That meaning is relational, that it depends on structure, connection, and shared reference frames, and that as the universe expands in scale and fragmentation, meaning becomes more distributed, less centralized, more fragile. In such a universe, civilizations may struggle not because they lack knowledge, but because they lack shared context. Even within a single galaxy, communication delays already fracture coordination. Within a universe governed by cosmic horizons, fragmentation becomes fundamental. This leads to a deeper reflection. Civilization as we understand it may be an emergent phenomenon that depends on a relatively small region of causal connectivity. Beyond that region, coherence dissolves, not because intelligence disappears, but because interaction becomes impossible. This reframes the role of humanity in a profound way. We are not observers standing outside a vast structure. We are participants within a local patch of a much larger reality, capable of understanding parts of it, but never fully engaging with its totality. And yet within that limitation, something extraordinary happens. We construct models that extend far beyond our reach. We map galaxies we will never visit. We describe cosmic epochs we will never experience. We infer structures that exist beyond observational horizons. This act of modeling is itself meaningful, because it shows that meaning does not require completeness. It requires connection between what is known and what is unknown, between observation and imagination, between finite experience and infinite possibility. As civilizations advance, their sense of scale expands, but so does their capacity to integrate that scale into coherent understanding. The universe becomes larger, but comprehension becomes deeper. This creates a paradoxical relationship. The more we learn about the universe's size, the more we recognize the limits of our position within it. Yet that recognition does not diminish significance. It refines it. It moves meaning away from centrality and toward participation. We are no longer at the center of anything, but we are part of everything we can access. And that access, however limited, is real. This is where cosmology and philosophy converge, because once scale becomes effectively unbounded, Questions of importance can no longer rely on spatial dominance. They must rely on relational presence, what we can influence, what we can observe, what we can understand, and what we can transmit forward. In that sense, civilization is not defined by its position in the universe, but by its ability to create continuity within it, even across centuries, even across light years, even across isolation. Meaning becomes a local structure in a non-local universe, and that may be its strength, because local structures can persist even in vast, indifferent environments. Stars are local structures within galaxies. Galaxies are local structures within clusters. Clusters are local structures within the cosmic web, and perhaps civilizations are local structures within an even larger informational landscape. In that framing, humanity is not diminished by cosmic scale, it is contextualized within it. We are not measuring ourselves against the universe as a whole, we are understanding ourselves as part of a hierarchy of structures, each operating at different scales of time and distance. And within that hierarchy, our role is not to encompass everything. It is to interpret what we can access. This leads to a final reflection in this section. If the universe is larger than any one civilization can ever fully observe, then every civilization exists inside a partial reality, a fragment of a greater whole. But fragmentation does not imply meaninglessness. It implies perspective. And perspective in turn becomes the foundation of understanding. So as we move toward the final section of this journey, the question is no longer simply how big the universe is. The question becomes how a finite observer can find coherence within an effectively unbounded reality. And what remains when scale no longer provides answers? Only perspective does. There is a final shift that occurs when a mind spends long enough contemplating scale. At first, the universe feels large in a physical sense. Then it becomes large in a mathematical sense. Then it becomes large in a historical sense. Then it becomes large in a causal sense, where even possibility itself begins to fracture under distance and time. But eventually something quieter happens. The sense of large stops being useful, because size requires comparison, and comparison requires a frame of reference outside the thing being measured. Yet in cosmology, there is no outside frame. There is no external vantage point from which the universe can be observed as a complete object. We are always inside it, always embedded, always partial. So the question, how big is the universe, slowly transforms into something else entirely. What does it mean to perceive something that has no external boundary? Earlier in this journey, we followed distances across the solar system, across interstellar space, across galaxies, and finally, across the observable universe itself. Each step expanded scale while preserving one assumption that we were moving through a structured container. But at the edge of modern cosmology, that assumption dissolves. The universe is not a container, it is the totality of spatial and temporal relationships from within which no external perspective exists. This makes the idea of size fundamentally different from everyday experience. A city has edges. A planet has a surface. A solar system has a gravitational boundary. A galaxy has a structural limit. But the universe, as far as physics can currently describe it, does not present an edge in the same sense. Even the observable horizon is not a wall. It is a limit defined by light, time, and expansion. It moves, it evolves, it depends on when and where observation occurs. So what remains is not a boundary. It is a field of possibility constrained by physics. And within that field, everything we have discussed exists simultaneously. Galaxies forming across billions of years inside the Milky Way. Expansion stretching space-time itself. Light carrying ancient information across incomprehensible distances, regions forever beyond causal reach, and regions still connected through gravitational structure, all of it real, all of it partial, all of it unfolding within a system we cannot step outside of. This is where the emotional meaning of cosmic scale changes, because the human mind instinctively searches for final answers, a boundary, a complete picture, a final map of reality. But the universe does not offer completion. It offers perspective. And perspective is not static. It expands with understanding. Each time humanity believed it had reached the limit of scale, something larger appeared. Earth became one world among others. The solar system became one system among stars. The galaxy became one structure among billions. The observable universe became one region within something potentially larger still. At no point did scale stabilize. It only deepened. This suggests something profound about the nature of knowledge itself. Understanding the universe is not about arriving at a final measurement. It is about continuously refining the relationship between the observer and the observed. In that sense, science is not a process that ends with answers. It is a process that continuously enlarges context. And that context always includes us, because every measurement, every observation, every inference originates from a single condition, a finite civilization embedded inside an expanding cosmos. From that position, we build models that extend far beyond what we can ever physically reach. We reconstruct galaxies from ancient photons. We infer cosmic history from faint background radiation. We describe structures that extend beyond any possible horizon. And yet those descriptions are not imaginary. They are constrained, tested, refined, and interconnected. They are attempts to map a reality that does not yield its totality, but reveals enough structure to be understood locally. This creates a unique kind of knowledge. Knowledge without completeness. Understanding without total access. Meaning without external confirmation. And still it works. We can predict cosmic expansion. We can trace the evolution of galaxies. We can reconstruct the early universe. We can identify structures billions of light years away, all from one small region of space-time. This is perhaps the most remarkable fact in this entire journey. Not that the universe is large, but that a local part of it is intelligible. And within that intelligibility lies something deeply human, a capacity to construct coherence from limited perspective, to find structure in partial information, to extend imagination beyond physical reach, or remaining anchored in observation. So when we return to the question that began this journey, its meaning has changed entirely. How big is the universe? It is no longer a question seeking a number. It is a question revealing the relationship between scale and perception, between reality and access, between existence and understanding. The universe may be finite or infinite, bounded or unbounded, observable or partially forever hidden. But in every case, it exceeds complete comprehension from within. And yet it remains partially knowable, not in totality, but in structure. And that structure is enough for meaning to emerge, because meaning does not require the whole universe. It requires only a connection to a part of it that can be understood. So as this journey ends, there is no final measurement to present, no ultimate number that captures everything. Instead, there is a perspective. The universe is larger than intuition allows, larger than observation can complete, and larger than any single civilization can fully contain within knowledge. But it is not unknowable. It is progressively knowable. Layer by layer, distance by distance, light by light. And perhaps the most important realization of all is this: we are not outside the universe, trying to measure it. We are within it, building understanding from the only position we can ever occupy. And from that position, even the vastness of everything becomes something we can begin to comprehend. Not completely, but meaningfully. And that is where the story of scale ends, not with a boundary, but with perspective that continues expanding as long as there is someone to ask the question.